Yes, so recording has started. So it's time. So yeah, would you start the first session?
Yeah, in a minute. It's about 2 minutes left. So,
Really?
yeah,
Yeah.
our director, Professor Sitaram, has joined also.
Good morning.
Good morning, Professor Sitaram.
Namaskar, Professor Ghosh.
Yeah. So, Professor Kuze from Tokyo Tech is co-organizer, co-convener, so to say. So,
Namaste. Mahai Gojamas.
so both of us have been in intense discussion over a couple of months about planning this program and so on and so forth. So we will be starting in a minute. Professor Rakhi Chaturvedi, I hope she is going to join soon. Yeah, Professor Chaturvedi is also there. So we can formally start. Professor Kuze,
Yes, please.
I,
Thank you very much.
shall I take over and start the
Yes,
proceedings?
please.
Okay. So, yeah, good morning to everybody over here at IIT Guwahati, and good afternoon to all the friends and colleagues from Tokyo Institute of Technology. It is a great pleasure to be finally able to organize this second workshop of physics departments of IIT Guwahati and Tokyo Institute of Technology. On behalf of physics department, IIT Guwahati, I welcome all our colleagues, our esteemed guests, our director, Professor Sitaram, uh, uh, Professor Kotaro Yamada, Dean of School of Science, Tokyo Institute of Technology, Professor Hidekazu Tanaka, Chair, Department of Physics, Tokyo Institute of Technology, and Professor Rakhi Chaturvedi, Dean Alumni Affairs and External Relations, IIT Guwahati, all the colleagues, all the students, all the participants to this 3-day meeting. I would very quickly show a few slides just to elaborate the scope of this meeting and the history of this meeting. So let me share my screen. Is it visible?
Yeah.
Okay. All right. So I formally welcome to this meeting. So this snapshot is basically, you can see that on the left is the famous temple from Tokyo, Asakusa Temple. And on the right-hand side, although Guwahati is famous for its Kamakhya temple, the Hindu temple, but I just thought that I will flash this picture. There is a Buddhist temple very close to IIT Guwahati. In fact, it's a few minutes ride over there. Not many people are aware of that, but there is the cultural similarity between these two institutes, two countries as well. So this workshop is not only just a forum for scientific discussion, but also kind of a cultural exchange as well. A bit of a history of this meeting is that in February 2017, Professor Paulos, the then head of physics department of IIT Guwahati, and Dr. Tapan Mishra, assistant professor IIT Guwahati, visited Tokyo Institute of Technology for a preliminary talk on a possible collaboration. And then in March 2017, Professor Nishida from Physics Department, Tokyo Tech, he visited IIT Guwahati, stayed here for about 10 days and signed a MOU between the two institutes. In November 2017, myself, Professor Saurabh Basu, and Dr. Tapan Mishra again visited Tokyo Institute of Technology to formalize the collaborations to maximize benefits of the MOU. And there we planned a joint symposium on condensed matter and high energy physics, because both the institutes had complementary expertise. And then we also decided that we should seriously think of collaboration between various research groups in the two institutes in various areas: condensed matter, atomic molecular physics, material science, gravity cosmology, and high energy physics. And we also understood that how we can do some student exchanges through several programs like MEXT and JSPS. Then in November 2019, 2 years after that visit, the first joint symposium on topics on condensed matter, high energy astrophysics and cosmology materialized over there at Tokyo Institute of Technology. It was a 2-day meeting. It was 23 lectures. We had 9 participants from IIT Guwahati. This is the picture of that workshop. It was a very cozy, homely kind of environment over there. And then we decided that the roadmap that we planned was that we will choose problems of common interest, start collaborations, we'll exchange personnel, which will eventually lead to joint publication. And then we can think of joint proposals attracting funding from agencies of the 2 governments. And as a part of it, a bilateral conference at IIT Guwahati in November 2020 was planned. But then this COVID-19 go ahead with our collaborations. And in fact, right now, to my knowledge, there are 3 collaborations which have been quite impactful. One is Dr. Tapan Mishra and his student Suman Mandal is collaborating with Professor B.P. Das and his student Ayuvi Haira over there on quantum phase transitions on dipolar bosons in WL optical lattices. Then Professor Saurabh Basu and his student Priyanka Sinha are collaborating with Professor S. Murakami, and they have a publication already in Physical Review B on transport in topological materials. Then Professor Devasis Bora and his student Devabrat Mahanta, they are collaborating with Professor Yamaguchi's group, and student Kohei Fujikawa is a co-author in their recent paper. Unfortunately, I couldn't find a photograph of Fujikura, so I couldn't put it. Instead, I put Professor Yamaguchi's picture just to make it symmetric. So these are the 3 collaborations, and I'm sure this meeting will sort of make our hand-holding stronger, and there will be many more collaborations coming up, and the plans that we had made would actually materialize in due time. So with this, I would stop my presentation, and I would like to invite Professor Rakhi Chaturvedi, Dean, Alumni Affairs and External Relations, IIT Guwahati, to share a few words.
Thank you very much, Professor Subradi, for a wonderful the welcome address, which is itself is an update on the conference, which we are foreseeing the webinar. A very good morning to Honorable Director, Professor T.G. Sitaram from IIT Guwahati, and the President of the Tokyo Institute of Technology, and my dear colleagues at IIT Guwahati and the delegates from the collaborating institutions, the students. Warm greetings and welcome you to this webinar. In fact, it is very motivating whenever we see the collaborations with the Japanese institutions. We are quite strong in these because most of the collaborations are with the Japanese institutions, and which we always enjoy. In the series, this is one of the 16 the Japanese institutions where we had a collaboration. We equally see the momentum in the activities under the MOU. I thanks to all the collaborators. With the Tokyo Institute of Technology, just to brief you about how we feel the AR office and how we enjoy the collaborations when it comes to the partner institutions. So with this Tokyo Institute of Technology, the MOU was formally signed in the year 2017, sometimes in the March, with the purpose of promoting the movement or mobility of the staff, the faculty members, mainly the faculty members, and the students, and also towards organizing the joint conferences, workshops, symposiums, with the added benefit of collaborations, the research collaborations or the teaching benefits from either side of the institutions. So the last year I could see exactly almost at the same time, sometime in November 2019, the first series of the conference, joint conference was organized. And very interesting to see that despite the pandemic around, we could see the second series of the conference almost at the same time is a partially 15 is a standard error plus minus 15 days is okay. So in the December 2020, again, we could see the collaborations, the joint conference. So this itself is a very, could see the momentum between the faculty members of the physics department of both the institutions. Although this time the conference is in a very new normal way, is an online, on an online platform. I'm sure you will equally, all of you and all of us will equally enjoy seeing the experts' opinion on the subject. Additionally, what I could see is 2 more topics have been added into the theme of the conference is cosmology and astrophysics, which is the buzzword in the physics, and it really will attract the attention of the students on these 2 topics, other than the condensed matter physics and high energy physics. What we see last time, as per the report of the conference in 2019, this joint conference, there were the 3 resolutions were taken. And I could see there were, all of them have been equally have been followed up and the momentum is maintained. Although slightly here and there because of it's all because of the limitations pandemic has imposed. First of all is a joint conference, one of the resolution, which is on time, very much on time, within 2020, and also the exchange of the students and the faculty member in terms of the research collaborations. The third one was the publications leading to joint proposals. And I could see from the updates of Professor Subradeep that both the departments are working on this. What else is needed in the MOU, under the MOU? It's very, very appreciative to both of the institutions and the faculty members. Thank you so much. And it really a big help to the Alumni and External Relations Office when we see the vibrant activity. I must congratulate and thank to all the organizers on either side for maintaining the activity in a very, very good, in an enthusiastic way. I wish all of you a very pleasant and memorable conference. And before I close, I would like to thank each and every one of you for attending this conference and bringing your expertise to this joint gathering. Thank you very much. Thank you very much.
Thank you, Professor Chaturvedi, for your very encouraging words. And in fact, we have gotten more than enough help from the External Relations Office. In fact, let me say that when the pandemic wasn't there, I had a talk with Professor Chaturvedi regarding organizing it here, and she gave us very nice suggestions. So hopefully sometime in future, we'll be able to really have a physical meeting over here with our Japanese friends. I would now like to invite Professor Kotaro Yamada, Dean School of Sciences, Tokyo Institute of Technology, to say a few words.
Okay, good morning or good afternoon. I'm so happy to meet you again here. But last year, we met together here in Tokyo and had discussion on science and some administration matters. And the discussion, it was fruitful. And I'm happy that this second workshop is one of the outcome of the discussions. I'd like to thank the organizers, both on India side and Japan side, for the effort to realize this second conference. Under this corona pandemic situation, our activities, research activities are so restricted so that this workshop should take place online. It seems unfortunate. In fact, we know that the scientific conversations in person, face-to-face, are important to develop revolutionary ideas, in particular for young scientists, as well as the senior people. So this form, online form of the workshop seems to be the second choice for Plan B, and I'm looking forward to the days that face-to-face workshop will be possible in near future. But this pandemic year gives us an opportunity to find a new way for scientific research, which may include a mixture of face-to-face and online discussions. We cannot stop scientific research under such a chaotic situation, so I hope this workshops makes a challenge and provides a good practice of new scientific research. Anyway, I hope all of you enjoy this great opportunity. Thank you very much for your attention.
Thank you, Professor Yamada, for your nice words. I now invite Professor Hidekazu Tanaka, Chair, Department of Physics, Tokyo Institute of Technology, to give his address.
So good morning and good afternoon, everybody. I'm Hidekazu Tanaka, the Chair of Department of Physics, Tokyo Tech. So first of all, I'd like to thank the members of organizing committee, particularly Professor Ghosh and Professor Kuze for organizing this nice workshop. So 3 years ago, the School of Science, Tokyo Tech, and Department of Physics, IIT Guwahati, has signed MOU to establish long-term collaborations. So this series of workshops is one of the activities based on the research collaborations. The first workshop was held at our institute in November the last year. The second workshop was supposed to be held at IIT Guwahati. So many members of our department were looking forward to visiting Guwahati. So however, unfortunately, the workshop was changed to be online due to COVID-19. So in the program of these workshops, 24 talks are scheduled. Speakers from both institutes present the latest research result. Those 7 talks are given by PhD students. The topics are very wide, ranging from the particle physics and nuclear physics to condensed matter physics and astrophysics. So I expect that this workshop will be fruitful and successful. Please enjoy the workshop. Thank you very much.
Thanks a lot, Professor Tanaka, for your remarks. I now invite Professor T.G. Sitaram, Director, IIT Guwahati, for his address to the workshop.
Thank you. Thank you, Professor Ghosh. Namaste. Very good morning to all of you in India and very good afternoon maybe in Japan. Professor Kotaro Yamada, Dean, School of Sciences, Tokyo Institute of Technology. Professor Hidekazu Tanaka, Chairperson, Department of Physics, Tokyo Institute of Technology. And Professor Ghosh, HOD, Department of Physics at IIT Guwahati. Professor Raki Chaturvedi, the Dean, AER at IIT Guwahati, and all my distinguished colleagues at IIT Guwahati and friends at Tokyo Institute of Technology. So I'm very happy to be part of this inauguration of the joint workshop by IIT Guwahati and Tokyo Institute of Technology. And it is almost more than 3 years of relationship between the two groups in a very important topic of condensed matter physics, high energy physics, astrophysics, and cosmology. As Professor Tanaka highlighted, is a wide area of research in the area of physics itself. So this initiative is a very laudable initiative. I congratulate my colleagues in tying up with one of the best known institute in Japan and working together. So at this moment, I would like to quote Henry Ford, coming together is a beginning, keeping together is progress, working together is a success. I wish the collaboration a great success between IIT Guwahati and Tokyo Institute of Technology. And I am very sure this will take the research in both countries to very greater heights. With these few remarks, I formally inaugurate this joint workshop between IIT Guwahati and Tokyo Institute of Technology. And I thank Professor Ghosh and his colleagues for inviting me to be part of this event on this day. I wish the workshop a great success. I hope all the delegates get benefited and with this interaction of 2-day workshop. Okay, so with these few remarks, thank you very much. Have a good day. Namaskar.
Thank you, Professor Sitaram, for your encouraging words. So now we formally close the inaugural session and we'll be moving to the scientific sessions. So before starting the scientific sessions and handing over the floor to the speakers and the session chairs, I would like to make a few announcements for everybody who are attending the conferences. First of all, this meeting is being recorded. I would first like to acknowledge the role of Tokyo Institute of Technology in a very on a crucial matter is that the webinar platform. The platform had to be comfortable for all the participants, the speakers, and then we tried few things and then we finally decided on Zoom. But then what happened was this, we do not have a subscribed Zoom software in the department. Then Tokyo Institute of Technology came forward and we are basically using their subscription so that we can have an uninterrupted session throughout the day. So for all the participants and everybody, this meeting is recorded and it will be published at the IIT Guwahati YouTube channel after the meeting. Then I would like to request the chairpersons and speakers to keep the time strictly because there are many talks and keeping time is very important. The talks are either 25 minutes with 5 minutes of discussion after that or 15 minutes plus 5 minutes of discussion. For the participants, I would request that it is better to ask the questions after the talk is over unless it is absolutely required to interrupt in between. And people can ask questions through the chat box as well. If time permits, the speaker will answer all right there. Otherwise, he can later on reply in chat box. And all attendees except speaker are advised to turn their audio and video off during the technical presentations so that the bandwidth does not become an issue. Okay, so with this, I would like to hand over the floor to the session chairperson, first session, Professor Masaki Uchida for the scientific session 1 on topological phases in condensed matter. Thank you very much.
Maybe we can wait until the scheduled time, I guess.
Yeah, I mean, meanwhile, the speakers can sort of get ready.
Test. Also, one remark is that on 17th, at the end of the session, we have a photo.
Right. Yes.
So everybody is encouraged to connect.
Everybody is encouraged to come and join in the photo session. We will actually, send sort of methodology to take the group photo in this web mode. Okay. So that will let know every participant. So we can wait for a few more minutes and Professor Uchida can take over right before 9:30 local time in India and 1 o'clock in Japan.
I just try out for a moment.
Yes. Meanwhile, you can try out this share screen and things.
Yeah, it's showing. All right.
Yeah.
Okay.
And Professor Basu, if you could switch on your camera, since we want to see the speaker.
Sure. Sure.
Yeah, I mean, all the speakers while speaking can switch on their video as well.
Okay.
But all others are requested to turn off their video and the audio.
Is it very cold in Tokyo now?
Yeah, from today, it's very cold.
Okay. Because even last year when we went in November, it was much colder than most parts of India at that time. So a month later would be quite cold. But does it snow in Tokyo?
Yeah, sometimes in January or February. Yeah,
Okay.
a few days.
Okay, I think the time is up. So let's start the scientific session 1, topological phases in condensed matter. I'm Masaki Uchida, chairing this session. So the first speaker is Professor Saurabh Bas, and the title is Tuning Topological Phase Transition in Chern Insulator. Please start.
Thank you, Professor Uchida. Thanks to all my co-organizers for making this happen. Special thanks to Professor Kuze for making this platform available at the last moment. In fact, it was it's really helpful for all of us. So I will talk about tuning topological phase transition. All right. In Chern insulators. Okay. And I'll show that how the topological properties can be controlled by deforming the bands, or rather, tuning the hopping amplitudes in a honeycomb lattice. We're talking about particularly of graphene. And just to put things in perspective, let us talk a little about the invention of graphene, not talking about the discovery. In fact, I quote Eva Andrei saying that graphene was invented much before it was discovered. So it was P.R. Wallace, who was a young postdoc just after the Second World War, who joined Atomic Energy Commission of Canada. And he was asked by his supervisor to calculate the band theory of graphite. And he tried for a number of years and he couldn't do it, actually. So even if you see that it's a band theory of graphite is the name of the paper, it's actually one layer of graphite that he was able to solve, which we know as graphene. So it's a honeycomb lattice of carbon atoms. And this is how graphene was born, but it was not discovered. And then several years have passed by, and there are people who have taken it off the closet, sort of presented it in whatever ways they have liked. One of the paper was Semenov. This was in '84, where he was talking about anomalies and in condensed matter physics. And then the most rather famous paper of Haldane, which is what my talk is based on, which he said that you can have quantum Hall effect without requiring Landau levels. You don't have an external magnetic field, but you still can have quantum Hall effect in a model of honeycomb lattice with a second neighbor hopping, complex second neighbor hopping, chiral hopping. And because of this work, he was awarded Nobel Prize in 2016 along with Kosteles and Thouless. And then, of course, in a very not too well sort of familiar fashion, graphene was discovered. It was people know about the Scotch tape technique, but there's an optical method by which graphene was actually discovered by Geim and Novoselov, and they were awarded Nobel Prize in 2010. That is that is about 10 years from now. And it was said that the atoms are on the surface, so there's nothing hidden. So manipulating properties of graphene should be very easy, and that was one of the things that have attracted the attention of the scientists. And the number of properties of graphene, which you all are familiar with, and these particular things, there's a very large Young's modulus and a tensile strength, which is very, very large, abnormally large, is what have caught the attention of many people who are working in the area. And as well, they are trying for applications, various applications, including medicinal industry, sports industry, and so on and so forth. So we sort of present this data for the reason that we want to actually calculate the electronic properties under some kind of a strain. And why strain is given is that, so graphene has been studied under strain, and one knows that really because of this large tensile strain, its strength, etc., graphene doesn't, it just stretches, and it says that you know, with a small amount of graphene, which you can hold it in your hand, you can probably cover a soccer field. So these kind of strains have been talked about in graphene, where the three hopping terms, graphene has three, honeycomb lattice has three neighbors. So one carbon atom has three of its neighbors, which are arranged in 120-degree fashion. So if you, the hopping terms, which are written as TA, TB, and TC here, if they follow a triangle inequality, then one has shown that, especially this paper by Hasegawa and Kishigi, they have shown that the Dirac points, they move, which are protected by the time reversal symmetry and the inversion symmetry, they move, but they survive. Okay. And strains have also shown to have important consequences in the optical conductivity of graphene. And here one shows that these blue curve that you see here, that shows a large optical absorption peak when it is, there is a there is some strains being given, which is shown by this angle phi, which really represents the direction of the electric field and the momentum vector direction, the angle between that. And so we take a motivation from this and turn towards Chern insulators. So this was in the Nobel Prize winning lecture by Haldane. Haldane said that it is later that he came to know that this Haldane model is also called as a Chern insulator. So it's just this honeycomb lattice with the second neighbor hopping, which are shown by this black lines with arrows. And red to red is, which is a clockwise hopping, is taken as positive, and blue to blue, that's taken as a negative, and there's a complex term there. So it breaks the time reversal symmetry, although without any magnetic flux being involved. Okay. And this M is just the Semenoff mass. It's pretty harmless, unless, you know, there are also some reports of having some importance attached to this Semenoff mass, but by and large, it doesn't interfere into the topological properties. So this model of graphene shows, or rather honeycomb lattice shows, quantized Hall effect without requiring any Landau levels. And this was something that had taken the community by storm. And in this paper, this 1988 paper, Haldane had shown that in this M phi phase diagram, phi is the phase, which is, we'll call it as a Haldane flux, and M is the Semenoff mass. There it shows a phase diagram which is marked by its the topological properties, and these the topological properties are seen here. In the blue region, you have a Chern number, and that's why they're called as Chern insulators. They have a non-zero Chern number equal to -1. And there is in the pink region or light pink region, there is a Chern number equal to +1. And in other regions of the phase diagram, the Chern number is equal to 0. So these non-zero Chern number regions are called as topologically non-trivial. So there are, you know, edge modes and so on. And C1 equal to 0 is called as a region which are topologically trivial. So they are trivial insulators, just the insulators we read in the first course on solid state physics. However, the pink and the blue regions are definitely not trivial insulators. So, so what we ask the question that what happens to such a scenario under deformation of the band structure? That is, if we play around with the hopping terms, then the band structure gets deformed. And in a model, in a Haldane model, that is a model with a finite Haldane flux, what happens to these kind of a system? So the question is rephrased as, can tuning the nearest neighbor hopping amplitudes help in elaborating or rather emphasizing its topological properties? And more importantly, whether a topological phase transition can be induced in this model. And we show a model of honeycomb lattice again, now not with 3 different hoppings, but there's just one hopping being different, which is shown as T1 along the green lines. So each blue is connected to 3 pink carbon atoms. All are carbon atoms, but it's a bipartite lattice, and one of them is T1. The other 2 hoppings are taken as T, and is a 2 atom per unit cell. So, and we want to know that what happens if this T1 is continuously tuned from a value equal to T to a value equal to 2T. Okay, and so we show the bands here for this T1 equal to 2T. And what happens is that there's something very interesting that happens at the M points. The M points in the Brillouin zone are just intermediate to the 2 Dirac points, which are often written with a K and K prime. And if you see the phase, see the band structure carefully, one sees that there is along the KY direction, there is a linear touching of the bands at that M point. And while along the KX direction is quite quadratic or parabolic, which you can see in the right figure on the smaller right panel. And so this has earned the name as semi-Dirac. So that's why we call it a semi-Dirac en route to band deformation, because it is in one direction, it acts like Dirac, in the other direction, it acts like parabolic, a 2D electron gas, so to say. So we, as I said earlier, that we have the motivation of introducing a Haldane flux into this deformed model of the honeycomb lattice. And we show it here that if you have no Haldane flux, that is what we just showed in the last slide, you have it, this semi-Dirac thing showing up on the left. And on the right, you have this, in presence of the Haldane flux, you have an anisotropic Dirac, and this is written here. And what we mean by anisotropic Dirac is that they are linear in both Kx and Ky directions, but the velocities along the Kx and Ky are different. So this is a very important digression from when you do not have a Haldane flux and when you have a Haldane flux. Of course, if you go to one higher order in the momentum, you'll see that similar features appearing. So this is only the low energy Hamiltonian. And so we show here the band structure by when the T1 is continuously varied from T to a value greater than 2T. So you see that, so for convenience, I've shown the Brillouin zone. You see the gap here. So this is called as the insulating gap, and it's a topological insulator. So these are the K and K prime points are the Dirac points, and M point is what is in between the 2 points. And as you change this ratio T1 by T, as I just reminding you that T1 is one of the hoppings of the 3 and the T is the hopping for the other 2. So as you tune that and you find that at this value T1 by T equal to 2, the bands actually touch. So the insulating property goes away and the bands touch. And the bands touch in a fashion which is in one direction. It looks like it's in fact the anisotropic Dirac for this particular case. Without the Haldane flux, it would be just a semi-Dirac, which we have said earlier that it's a linear in one direction and a non-relativistic parabolic in the other direction. And as you continuously tune T1 to greater than 2T, again, the gap opens up. There's a close-by view of this, a zoomed view of this. And so we asked the question that these insulating phase at in the first figure on the right and the one that is in the left of the last figure, Is there anything interesting happening there? Both have gaps. And we see that indeed there are something interesting there. We look at the DOS, the density of states, the single particle density of states is a nice gap at T1 equal to T. And there are additional Van Hove singularities appearing here and so on. These singularities nearly, the additional singularities nearly go away to a value which is close to 2. And at 2, the density of states closes. Of course, this has a different analytic form close to the energy value. And then again, there is a small gap that opens up. And so basically these additional peaks, as I said, they are from the Van Hove singularity, which arises from the saddle points in the spectrum, in the single particle spectrum. So in order to understand the topological properties, here we take a finite size ribbon and again do the band deformation, and you see this red line actually cuts the bands, the edge modes rather, at 2 different positions, U and V. And the same thing continues all the way till about, this is 1.9. And that figure is represented by this yellow panel down there on the left, where the red arrow and the blue arrow, they show that there are 2 counter-propagating modes, which simply talk about the quantized Hall effect that we are familiar with. As you go to a value T1 equal to 2T, which we call as the semi-Dirac limit, in fact, this is not for a large ribbon, so you see a gap. In fact, this gap closes as the size of the ribbon increases. But now you see that there are 4 points. But indeed, this band, the edge mode that you see below, actually gets, or rather, both these things, both these modes, that they get merged into the bulk. And as you cross that value, the semi-Dirac value, which is T1 equal to 2T, you see that there are 2 modes appear per edge, like the one in the yellow panel on the bottom. And this, of course, they'll cancel each other and there'll be no Hall effect there. And this is what we see. These are written there at less than 2T, you have all these counter-propagating modes. So you have quantized Hall effect, and this T1 equal to 2T, there's something very interesting happening there. And this is what we want to probe more closely. So we look at the different topological markers called as the Berry curvature, which is defined as these expectation values of these velocities. And this A is called as a Berry vector potential. And they are plotted here again for different values of T1, which is one of the parameters that we tune. And you see the Dirac points, the values are concentrated around the Dirac points. And what happens is that as you come close to T1 equal to 2T, you see the values which are concentrated along the M point, and they are really at the M point there. And this, of course, we have plotted just before the value T1 equal to 2T, because otherwise it becomes undefined. The Berry the curvature becomes undefined. So to understand these things better, we also calculate the Berry phase. And the Berry phase, so this is the Dirac case where T1 equal to T. So in general, so Berry phase, just to remind everyone, that is the phase picked up by the electrons when it goes round certain point. It's an irreducible phase, unlike the dynamical phase. And it should not depend upon what is the energy of the electron. So as long as it takes the tour of the point under consideration, it should not depend on the energy. But it does in presence of the Haldane flux. This red and blue, they denote the Berry phases for the conduction band and the valence band for different energies. And so this is the semi-Dirac, which is T1 equal to T2. The variation is different, but not only that, if you look at the values at E equal to 0, then you see that these values are too different. So this is 2 pi, which is like a non-relativistic electron gas, 2D electron gas, or just non-relativistic particles. And this is 0 means the same thing. That is when it comes around, it picks up a value 2 pi, which means that it doesn't pick up anything. Whereas this is a signature of the relativistic electrons, which are called as the Dirac electrons. So this thing would not have been clear unless, this is all in presence of the Haldane flux. So the electrons really behave very differently in presence of the Haldane flux. And we show it, so at very low energies, there's a value 2 pi here, whereas there's a value pi here for the semi-Dirac case. And in the Dirac case, there's a value 2 pi. And this is what is written there. And so we show the the Berry phase and how it actually falls off as a function of T1 by T. In the inset, you may not see this very well, that even this is not absolutely, this top line is not absolutely smooth. There is a small curvature in that. So, and then of course, it at a value T1 equal to 2T, it falls to a value pi. This is what was shown in the earlier plot. So in the Dirac limit, of course, it corresponds to a 2D electron gas. And in the semi-Dirac, the relativistic nature of electrons, which are known as the Dirac electrons, are recovered. So we finally show the Chern number. There's the same plot that Haldane had shown. The first plot is same as Haldane's plot. So the blue one corresponds to Chern number equal to -1. So here it says blue equal to -1 and red equal to +1, and green corresponds to 0. And as you tune the band, that is, as you deform the band, then these Hall lobes, the width of the Hall lobes, that shrink. And at a value T1 equal to 2T, the width completely goes away, which we can't show. Everything becomes green, that is. But even just before the value T1 equal to 2T, there is a small width that is seen there. So this is the feature or the signature that actually there is a topological phase transition that is coming. And the Chern number is defined in this fashion, which is the integral of the Berry curvature over the Brillouin zone. So this ds is nothing but the Brillouin zone over the Brillouin zone. So it's a surface integral of the Berry curvature. And so the system is transiting from being topological to non-topological across the semi-Dirac point. And this is what is shown there. The Chern number all on a sudden drops to 0 at the value T1 equal to 2T and stays there all the while after that. And so it just, there's absolutely, so even at 1.99 or even closer to 2, it stays at 1, which means that the system is a topological insulator. And as it goes to 0, it becomes a trivial insulator. And Chern number is a nice marker of that. And we know from this Gauss-Bonnet theorem that the Chern number is related to the anomalous Hall conductivity. We call it anomalous because there is no magnetic field there. Anomalous Hall conductivity. And this is the Hall conductivity plot. The red one that you see here, which is for the Dirac case, and you see a large Hall plateau, which is a signature of Dirac physics. And as you tune the band, that is, you change T1, we see that these anomalous Hall plateaus shrink farther and farther. And at a value which is T1 equal to 2 or just beyond that, it becomes equal to 0. So no Hall effect means that we get a trivial insulator, and which is also told from the plot that we have shown for the edge modes. So the quantum Hall effect vanishes for the edge modes. So even if you have a gap, it's not there's no guarantee that it will give rise to quantum Hall effect or it will give rise to topological insulator. It will be a trivial insulator in that case. So the Hall plateau vanishes at T1 equal to 2T, and and we have this energy gap width that is shown by the red line. So the energy gap actually goes to 0 at T1 equal to 2T, and then again rises, whereas the green points are actually the plateau width, which doesn't rise after the semi-Dirac point, and it continues to be 0. So this is again saying the same thing. Coming to the conclusions of the talk, which is we have seen topological phase transition induced by the band deformation in a Haldane model. And the system undergoes a phase transition from a topologically insulating phase to a trivial insulator. And we have used different topological markers such as Berry phase, Berry curvature, Chern number, etc., and also anomalous Hall conductivity in order to track down the phase transition. And thanks to all the collaborators, Shayan Mandal is a PhD student here. Dr. Priyadarshini Kapri was a student in the department and is now a postdoc at IIT Kanpur. Bashab Dey is a student at IIT Kanpur. Professor Tarun Kanti Ghosh is professor at IIT Kanpur. And I gratefully acknowledge many illuminating discussions on the semi-Dirac physics, chiral anomaly, etc., with Professor Murakami of Tokyo Tech, Professor Bhaskaran, who was at IMSC, and Priyanka Sinha, who's another graduate student in the department. And so this is a beautiful campus, which we all wanted you to be a part of in this year, but unfortunately it's not to be. And thank you for your attention. Thank you.
Thank you for the wonderful talk, Professor Saraba.
Thank you.
Now the talk is open for discussions. You have... Oh, please, Professor Pankaj.
Yeah, so Saurabh, it was a very nice talk. So I was just wondering, I have two questions. First, related with that, what is so special about T1 equal to 2T? And second, when the energy band energy width basically goes to 0 at T1 equal to 2T, have you looked at the things that whether it is power law or it is something else?
Power law for the density of states?
No, energy gap is going to 0 at T1 equal to 2T. So
at T1 equal to 2T, I believe the energy gap goes linearly to 0, which is probably almost clear from this. So this red is the energy gap. And so this is your first question is very interesting, that why what is this particular thing about this T1 equal to 2T? So this was, in fact, people have started looking at this in the Floquet formalism, where so as you change one of the hoppings, which you can also do it by an external field. So as you change this hopping, since you do not do anything to either the time reversal symmetry or the inversion symmetry, the Dirac points, there's no gap opening at the Dirac points. The Dirac points simply move, but they survive. Now, at this particular point, the movement, they move and they merge. The two Dirac points merge at this point in between. They symmetrically move, and as exactly at 2, again, the two Dirac points become 1. So basically the Dirac electrons are gone, and instead it gives rise to a very strange dispersion, which is linear in one direction, and it's quadratic in the other.
Okay, thank you.
Thank you.
Any questions or comments? Actually, yes, I have one question. So do you have some material candidate for such a semi-Dirac system
Yes,
other than graphene
yes,
or
yes. So the vanadium oxide VO2 and the layers of that are good candidates, and there are some organic salts also which shows a dispersion which is very, very close to the semi-Dirac dispersion. And not only that, phosphorine, which is again known to be a single layer material made of phosphorus atoms, which is a layer of black phosphorus, shows somewhat semi-Dirac dispersion, in the sense that the Landau levels, etc., they are very close to the semi-Dirac. So there are a number of things which one claims that they have a semi-Dirac dispersion experimentally achievable.
I see. Thank you so much.
Thank you.
If there are no questions, I think let's move on to the next speaker. Thank you so much
Thank you
for the wonderful talk.
Thank you very much. Thank you.
Okay, the next speaker is Mr. Shriman Mandal, and the title is Topological Inheritance in Half SSH Hubbard Model. Please start.
Yes, yes. Share my screen.
Okay, we can see the slide. And
yes, and let me make it full screen. Yeah. Okay, thank you, Professor Uchida, and hello everyone. Today I'm going to talk about the topological inheritance in half-SSH Hubbard model. So other than me, there are three more people involved in this work. Dr. Tapan Mishra, my PhD guide, Professor Luis Santos and Sebastian Gessner, our collaborators. So topological phases of matter can show some exotic properties. So for example, it can have a conducting A state where the bulk is insulating, but also the excitation in the system can have fractionalized units of charge and spin. Also, these systems can have degenerate and entanglement spectrum. These properties are very robust against disorder and perturbation in the system, and because they are protected by topology, which is related to some integer number, which are called topological invariants, and this term topology was first introduced in mathematics to describe the shapes of the objects. And this says that when two objects are topologically similar, then they can be smoothly deformed into each other. But if we want to deform a topologically different object to a topologically different object, then we have to do something violent, and we have to poke a hole into the system. For these cases, the topological invariant is called genus, and this genus is given by this formula, which is a Gauss-Bonnet theorem, and this is given by integral over the Gaussian curvature over the closed surface. And this abstract idea was introduced in the condensed matter theory to describe the energy bands of the physical systems. For the case of Chern insulators, these topological invariants are called Chern numbers, and they are given by the the integration over Berry curvature over the Brillouin zone. And these non-trivial topological invariants, which are called Chern numbers, are actually responsible for the quantized number of A states, and which is further responsible for the quantized Hall conductivity in the system. So after the discovery of the quantum Hall insulators, there are scientists have discovered 1, 2, and 3-dimensional system where this Hall conductivity can be seen. And today I will only be restricted to the one-dimensional system. For that, I will first introduce a Sussi-Perheger model. Then I will talk about how symmetry and topology comes into the picture. Then I will introduce a model which we call half-SSH Hubbard model. Then I will show some interesting result, and then I will conclude my talk. So first of all, the SSH model is a very simple one-dimensional model that shows topological properties, topological phase transition in the system. And this was first introduced to describe the polyacetylene chain, where the electrons have staggered hopping structure along the chain. And this kind of model become a very popular system to study topological physics, because this can be very easily simulated in quantum simulators such as alta-cooled atoms in optical lattice and photonic systems and superconducting circuits and so on. For example, in optical lattices, with the series of double potential, this potential can very easily mimic the SSH model. The SSH model Hamiltonian is given by this, and the T1, T2 are the staggered hopping amplitude along the chain. So then the symmetry that protects the topology in this kind of system is called chiral symmetry, and this chiral symmetry can be violated by introducing some diagonal term in the Hamiltonian, or with long range hopping in the system other than the nearest neighbor hoppings. The consequences of chiral symmetry is that the system also has sublattice symmetry, and every state with energy E comes with the chiral symmetric state which has the energy minus En. And if you look at the band structure, because this system has two-side unit cell, the band structure has two bands, and in this band structure, when we can see that when T1 is less than T2, when T1 is not equal to T2, for the case A and C, both the system is gapped, but when T1 equal to T2, the system is gapless at the point. But if and these two gapped phases are topologically different, which are defined by the topological invariant called winding number, which is 0 for this case and 1 for this case, and in between there is a gap closing. So if you look at the finite kind of system, and if you tune the chemical potential to the 0, then for finite system we can we see that the system is dimer insulator, where one of the particle is getting dimerized in one double well potential, and when T1 becomes equal to T1 equal to T2, then the system becomes gapless, and we see a long range coherence in the system. And when T1 is less than T2, we see that in the bulk the system is same as this this state, but there is a state sitting at the edge. To see that more mathematically, we have calculated the energy spectrum. We have looked at the energy spectrum. As you can see that when T1 is less than T2, I have considered only L equal to 20 sites. I mean the length of the system is 20, and I have considered T2 equal to 1. As you can see, when T1 is less than T2, we see a zero energy state. When we plot these states, we can see that they are localized at the edges. So these are called localized edge states, and when T1 is greater than T2, the system is again gapped, but the states are not localized at the edge. So these kind of edge states are very robust against hopping disorder, and this and stays in the zero energy. But when we introduce on-site potential in the system, that breaks the chiral symmetry, and the edge states become energetic. Okay, so now I will introduce the model which we have considered to study this work, to perform this work, which is we call half-SSH Hubbard model, where we consider a two-component system. When one of the component is subjected to SSH kind of dimerization, but when the other component is along the chain have a normal and homogeneous hopping, and these two components have the interaction energy U. For the calculation, we have considered two-component Hardware bosons, which shares the same energy spectrum and diagonal correlations with fermionic systems. We have used a numerical exact method called DMRG to solve the half-filling case. So this kind of system can be realized in optical lattices with the state-dependent optical lattices, and also we can consider two decoupled chain. And in the decoupled chain, the interaction along there will not be any interaction along the chain, but there will be interaction along this direction. And this interact with the long-range interaction, and this can be realized with the dipolar bosons. So if two dipoles are polarized to a certain direction, the interaction potential is given by this, and we can tune this theta to make the interaction along this direction 0, and again this will have some interaction along this direction. So in this model, we have solved the Hamiltonian at the half filling, and we have considered T1 equal to 0.1 and T2 equal to 1. That makes the up component topological non-trivial, and T equal to 1, which is a normal trivial system if there is no interaction. So to see the bulk properties, we have to see the dimerization in the system. We have calculated the dimer structure factor at the value k equal to pi, and we have calculated the gap in each component. So as we can see that when for the up component, which is given by the blue lines, the gap and the dimer order is always finite because this is not topologically because this is always a gap phase, and for the down component, we can see that when there is no interaction, the gap and also the dimer structure factor is 0. But when we introduce some u, this becomes the gap both becomes finite and also the structure factor becomes finite. So as you can see that in both the both the direction, when u negative and u positive, they are symmetric, and we have just only looked at the attractive cases, which can be easily translated to the repulsive cases. So then again, we have looked at the pairing in the system. So to do that, we have calculated the eta, which is given by this formula. And in this case, we can see that when for the attractive case, for very large attractive interactions, we can see that this value is approaching 1. That means the two component is becoming pair. One particle from the up and one particle from the down component is becoming pair, and for u equal to 0, there is no pairing in the system. And similarly, for the repulsive case, we can say that similar thing. So for the strong pairing limit for u, when u is very large, we can map the Hamiltonian, the original Hamiltonian, to this Hamiltonian with renormalized hoppings, and this p are the pairing pair annihilation operators. So as you can see, this model is also similar to the SSH model. So we can say that for large values of u, the whole system is actually topologically non-trivial, and at the same time, the down component is also topological non-trivial, which is inherited this topological property from the up component for the interaction because of the interaction. So the question we ask is what happens when the interaction is very less and the pairing is very weak. I mean, in this kind of region. So to do that, we have looked at the topological properties in the system. So first, we have looked at the edge states in the system. So as you can see, for large attractive interactions, in both the component, the edge state is present. The particle is localized in a particular edge, and we can quantify this A state by calculating the real space polarization. And if the polarization is minus 0.5, that means one of the particle occupies the one A state which is at the left. So that gives you polarization minus 0.5. And as you can see, for lower values of interaction, around 1, the full inheritance is happening because the value is approaching 0.5. So this value is maybe around 1, minus 1. Also for repulsive cases, it is around 1. Okay. So then we have looked at the dynamical property of the topological non-trivial system, which is called a topological Thouless charge pumping, which has a good analogy with the Archimedes screw pump. As you can see from the figure, that by rotating this steering, we can pump the liquid from the reservoir, and this kind of situation can be simulated in the quantum mechanical system by varying the what is that called, the parameters of the Hamiltonian periodically. So in the SSH kind of model, this kind of pumping can be realized with the Rice-Milling model with the introduction of this new term, which is the on-site potentials. So in this scenario, if you look at a particular cross section of the system, and if you vary the T adiabatically, then you can expect that one quantum of particle should transfer to the other side. And this only happens if the system is topological non-trivial. This kind of pump has been realized in the experiments by the group Takahashi in Kyoto and Immanuel Bloch and so on. So if we look at the finite size system, okay, and if we consider our model where only the one component is being derived with this Rice-Millie kind of model, and other component is always homogeneous and non-trivial system. And with the introduction, we want to see with the interaction, we want to see how this topological charge pumping is induced in the down component, which is non-trivial. So for finite system, we can track the charge pumping by looking at the edge state. So for when this adiabatic parameter tau is 0, the edge state should sit at one edge. But when the tau is 2 pi, sorry, tau is pi, then we should see that the edge state is transferred to the other edge of the system. So to track that, we have calculated the polarization in the system again, and the integral over this polarization gives the number of charge pumped per cycle. So as we can see, for topologically non-trivial system, which we have considered for the up component, is always shows a robust pumping for any values of u. But if we look at the down component, we can see that for zero interaction, there is no pumping happening, but with interaction, when we increase the interaction, the pumping is happening. And if you look at this value u equal to 1, after that point, we can say that the complete and robust pumping is happening. So from this slope, initial slope of these curves, we can actually quantify when the actual full topological pumping is happening in the system. So we have plotted that value, the initial slope of this pumping, and we can see that around u close to 1, the curve shows some different behaves something differently, and we can mark that point as a topological inheritance point, which is very low around value 1. So to finally quantify the actual point for the thermodynamic at the thermodynamic limit, we have calculated the fidelity susceptibility, which is actually the differentiated form of the inner product between a two-wave function at two different parameters. As you can if this value shows a peak at a certain point, that means this can be the point of phase transition. Okay, so we have calculated that only for different values of L, I mean the system size, and we can see that the peak position is shifting towards this value, which we have calculated from the extrapolation of these values, extrapolation of these peak points. So as you can see that the complete topological inheritance can happen at value minus 1.6 for the recursive case. At the same time, we can say that for recursive cases, it will be plus 1.06. So in this slide itself, I want to conclude my talk. In this talk, I have shown that when the interaction is very large, which is very intuitive to think that the system behaves non-trivially, but when the interaction is very less, then we can see that there is a complete topological inheritance in the system where the pairing is very weak, where the eta value is close to 0.2 or so. So with that, I'll thank you everyone for the attentions. Yeah.
Thank you for the nice talk, Mr. Shima. Now the talk is open for discussion.
Can I ask a quick question, Girish?
Yeah, sure.
Hello.
This is Shumant.
See.
Oh yeah. Okay. Sure.
Got it. See, I'm a little bit hazy about this DMRG. Exactly what are its limitations? The point is that it's very good when the system is gapped, but when we say gapped, there are two possibilities. One is that there is a gap between the ground state and the first excited states, or there are gaps between all the states. Say, for example, particle in a box, all states have gaps in between them. But then if you take, for example, a lattice, which is, infinite in extent, that you can have, so if you have a finite system and a lattice, then it will be like particle in a box, all states will be gapped. But if you have an infinite lattice, then you can have a gap between the ground state and first excited state. So which one, which of these is better for DMRG? Are both equally, is DMRG equally good for both the systems or only one of them?
For the DMRG calculation, it is very efficient to calculate the ground state only, but you can calculate the higher excited state up to maybe 2
No,
or
no,
3
that's
with
not what
very
I'm
good
asking.
approximation. Yeah.
No, I know that, but what I'm asking is that, you know, it has been said many times in literature I've read that DMRG works well for gapped systems. But what I want to know
Okay.
is that gapped means what exactly? Is it gap between ground state and first excited state? Or is it like particle in a box where all the states have gaps in between, not only ground state and first excited state?
No, the gap in the system is actually the charge gap in the system, which is number of particle in the if the energy states, I mean the if you try to fill the system with number of particles, the gap between those energies are the actual gap in
Means
this kind of
all
system.
the states have to have gaps in between them, not only the ground state and first excited state.
Yes.
Usually gap means that only, ground state and first excited state. Anyway, maybe somebody else can ask.
Any short comments or questions? If not, now the time is up. So let's thank the speaker again. And we will move on to the last speaker in this session. The speaker is Professor Shuichi Murakami. And the title is Topological Materials and Higher Order Topological Materials.
Okay, so can you hear me?
Yes.
Okay, and can you see the screen?
Yes.
Okay. Oh, okay. Thank you very much. Okay, so thank you very much for the introduction, and yeah, I would like to thank the organizers for giving me this opportunity. So, and first of all, I would like to appreciate this say collaborated say collaboration between the IIT Guwahati and Tokyo Tech. So yeah, yeah, I collaborated with Professor Basu and we published one paper jointly, and it is really thanks to this say project. So so this work is in collaboration with these people. Let me see. So these people, these are the present and the former member of my group, and it is also a collaboration with Professors Matsuisha and Hosono also in Tokyo Tech. Okay, so let me give you an outline. So I first give some introduction on topological insulators, which previous speakers has also given a nice introductions. And then I will give some of the results of our recent research results. So yeah, I have been doing various things about topological insulators, but maybe for some people who are not so familiar with this topic, let me give you some kind of real material example to see what is going on for this topological insulator physics. So I would like to present two topics. One is the electrolyte material, which is important in chemistry, and the other one is the action insulator, which has been intensively studied recently. So let me give you some introduction. So yeah, just very briefly explain. So this is in fact also we have shown in the last week last year the conference last year. So this is an introduction of the topological insulator. So it is insulated in the bulk, but the surface or the edge is metallic due to some topological nature of the wave functions. And in this case, it's caused by spin-orbit coupling. So, and in this case, the surfaces conduct the pure spin current. And yeah, so the important thing is that this kind of a metallic surface state comes from the topological nature of the wave function, as also previous speakers has pointed out. So in this case, wave functions can be classified. The insulator wave functions in the insulators can be classified by some integer number called the topological number. And say in this case, for example, the Z2 topological number classifies this state, and whether it is 0 or 1 corresponds to the normal or the topological insulator. And yeah, for example, so this we also have shown last year. So this is one of the proposals we made. So for example, if we make a bismuth bilayer system, then it will be a say two-dimensional topological insulator, as I shown here, like that. So the interior is the bulk is a insulator, but the edge is metallic, and it has been shown in experiments in this shown here. Okay, so from that, we studied several kinds of material aspect of such kind of a topological insulator. For example, in collaboration with Professor Hosono and Matsuishi, we are studying the material class called electrolytes. So electrolyte, maybe some of you may not be so familiar with that. So electrolyte is a material where electrons in an interstitial region act as anions. Which means that so this is one example of electrolyte. So in this case, these balls are atoms, but the electron layer is not close to the atoms, but it is in between the atomic layers. And these electron layers is like negative ions in ionic crystal. And yeah. So in previous paper, we proposed that such kind of electrolyte material can be a good platform for topological materials. So we propose that there are many electrolyte materials which are topological, and in these cases, it can be also chemically important. Because so if it is topological, then such kind of electronic wave function is away from atoms like that. So this means that such kind of electrons can be active for example, for the chemical reactions. So one example is given here. So this is a scandium 2C. So it is Y2C, but the scandium Sc2C is also the same crystal structure. So this is a bulk band structure. So it means that this is a Fermi energy. So there's no Fermi, there's no state at the Fermi energy, and it's insulating. But if we consider the slab geometry with a surface, then there's a extra state here, which is absent in this figure. Which means that this is and this we can explain originates from the topological nature, in fact from the Zach phase. And so this is also a kind of related with the SSH model, which a previous speaker has mentioned. So in fact, this pi Zach phase is the same topological number as a SSH model. So this state is also corresponding to the SSH type mid-gap state. And this surface state is shown here. So in this case, this electronic state is here for this state, and and this is somewhat away from the atomic layer. So such kind of electrolyte material have various examples. For example, we studied this kind of apatite family, which has this kind of a chemical formula. So this is electrolyte. This is a 1D electrolyte. So this means that there's some interstitial electronic states in the 1D, forming a 1D channel like that. Okay, so So this is a figure from above. So this yellow region is a hollow space for atoms, but there are electrons inside this hollow, which is schematically shown here. So this is an electrolyte, and then if we say, for example, make the system to have a surfaces. So if we have a slab geometry, namely if we make a kind of thin film out of this, then there's a surface, and this is a band structure. So, and this yellow line is a Fermi energy. So this means that there's no state at the Fermi energy, and this system is insulated still. And yeah, it can be seen from the simple argument. So from a detailed calculation, we can show, so this is a schematic picture, but we can show that these interstitial region has a filling number 2. So this figure corresponds to this figure. And these dots are interstitial electrons, and this has a filling 2. So if we have a surface like that, then the filling is halved, which means that the filling is 1. But as long as the filling is an integer, this is insulating. But something different happens next. So suppose we consider this kind of, say, a hexagonal cylinder, then each corner is divided by 1/3. So this means that at the corner of this hexagon, or so this is the whole kind of schematic of a whole system. So this has this kind of corner, and at this corner, the filling is it becomes 2/3, which is a fractional, meaning that the hinge. So this corner is metallic. So this is the first method of calculation. So it means that there's some hinge state which crosses the Fermi energy, and it is a 2/3 field. So this means that if we consider this kind of a crystal, then the corner becomes metallic, and such kind of a metallic state also comes from the topology, and this is one of the example of a higher order topological insulator. So yeah, and in fact, there are many families of a higher order topological insulator, and I cannot explain all the families, but I explain here the case where the charge is trapped at the hinges on the crystal like that. And in other papers like this paper, the sodium chloride, NaCl, it has a quantized corner charge at the corner like that. And on the other hand, we also studied another type of a higher order topological insulator called action insulator. So in this case, instead of trapping charge, in this case, it has at the hinge, there's a current like that. So this is a whole crystal, and it is insulating, but there's a metallic state going around the crystal in this way, and this is chiral. So it goes in a one-way manner. So yeah, in the latter half, I study this one. So so this is the action insulator. So so action insulator might sound kind of a unique name. So action insulator comes from the elementary particle physics. So if we have this kind of action, this kind of a form of the action, where electric field and magnetic field are coupled to each other, then there arises some response where the magnetism and the electric field response are kind of crossed to each other. So if we apply the electric field, it induces the magnetization, or if we apply the magnetic field, it induces the polarization. and the interesting thing happens when if there's some symmetry, then this theta is quantized to be 0 or pi. So of course, in almost all the cases, theta is 0, but in some cases, theta might be pi. So people have been searching for system where theta becomes pi. And this is known that this is quantized to be 0 or pi, either with an inversion symmetry or by time reversal symmetry. So if we say, for example, initially there's some effort to search for such kind of system with a time reversal symmetry. But in fact, there's experimentally it is somewhat difficult to achieve this in reality. So there's some effort for searching for such kind of a material with inversion symmetry. So let me remind you that either inversion or time reversal symmetry should be present for theta to be quantized. So instead of this time reversal, another strategy is to preserve the inversion symmetry. So in that sense, there are some material which has been proposed to be action insulator. For example, these materials. So these materials are layered anti-ferromagnet. Namely, they are layers, but they are like a up-down oriented magnetization. So in this case, so whether or not it is an axion insulator or not can be calculated from some kind of a topological number. And what I would like to say is that this condition is the same as that for the higher order topological insulator, so which has been shown in previous papers. So there's some details. So let me just skip the detail. But the important point is that if we know the wave functions, then we can determine the parities of the wave function. So if it is either symmetric or anti-symmetric with respect to the inversion, then from that we can know the so-called Z4 topological number. And if we once know the Z4 topological number, and if it is 2, then it is action insulator with a quantized ME effect, magnetic effect, and at the same time, it is a higher order topological insulator, which is like that. So they are the action insulator and the higher order topological insulator are the same class of systems. Okay, let me explain. So, but in fact, it is not easy to see why Z4 equals to 2 give rise to this, say, existence of a metallic hinge state. Or in other words, whether if we know the parities, so if we know whether the wave functions are like this or like this, determines whether there's a hinge state or not. And we consider this problem in these two papers. And I just skipped the detail. But the important point for this argument is that we say gradually say change the boundary condition of the system. So suppose we begin with a periodic boundary condition, and then we gradually cut the system at the surface, and the intermediate state is an open boundary condition. Then after that, it goes into the anti-periodic boundary condition by changing the value of the hopping across the boundary. So by doing this process and follow the spectrum change, then we can see that there's some this kind of a relationship. So I also skipped some detail, but the point is that if we have such kind of a Z4 equals to 2 insulator, then if we cut this system, into a two-dimensional slab like that, then it is always the Chern insulator with a chiral edge state. So this chiral edge state is nothing but a hinge state in this kind of a system. So it means that if we to sum up, if we have an insulator with d4 equals to 2, there should be always a hinge state like that. So from that kind of knowledge, let me explain the final topic, which is how the position of a chiral hinge state is determined in higher order topological insulators. So yeah, so this as I said, this is a crystal, and the hinge state is like that. But this is just an example, and so there are many hinges. For example, here, but some hinges support the hinge state, but some do not. So we are interested in what kind of which hinge support the hinge state, and this is determined by the surface orientation. So for example, if we consider the spherical sample, so this is a sample which is a spherical, then each point on the sphere has a different orientation of a surface. And depending on the surface orientation, we can define the surface mass. So if m is 0, then it is a massless, so gapless metallic state. And if it is non-zero, then the surface is insulating. And the important point is that this m is shown to be odd under inversion symmetry. So it means that at some side, m is positive, then at the other side, m is negative. So in between, there should be some line where m equals to 0, where the chiral hinge state lies. So in this hinge state reflects the symmetry of the system. So if the symmetry of the system is very high, for example, if it has a cubic symmetry, then the metallic hinge state is determined from this symmetry. So we can classify these in terms of the symmetry. And yeah, so from that kind of a study, we study this kind of a material. So this is a layered anti-ferromagnet with a up, down, so layered material. And in this paper, this is shown to be Z4 equals to a higher order topological insulator with this kind of a hinge state like that. So this is a crystal, and along these hinges, this has a hinge state. And from our classification, in fact, this corresponds to this case. So hinge state has this kind of a C3 symmetric zigzag type configuration. And this, in fact, corresponds to this, to C3 symmetry. Yeah, and we note that this is a kind of up-down layered compound. And from symmetry analysis, we can conclude the following generic conclusion. So in the odd layered case, where the magnetization is up, up, then the hinge state is as shown in the previous page. Like there's one loop here. But if it is an even layered anti-ferromagnet, like up, down, then the hinge state configuration is different like that. And there are 3 loops of current. And it is due to the fact that the magnetization, in fact, changes, determines the surface mass. So this M corresponds to the magnetization, in fact. So in this case and this case, the lower surface here and here, the magnetizations are different. So this is up, this is down, and this changes how the current flows on the lower, say, surface of the cylinder. So in this case, this changes to this, and this current loop changes to 3 loops. So in that sense, there's some unique, say, dependence of the odd or even layered or material. I mean, layer number. So we can also have a numerical calculation, which is in the same symmetry class as this previous material, like this one. Then we can easily see from numerics that in the order layered case, the hinge state appears here and here. So this is some cut of the intersection section of the system. So in this case, the hinge state appears here and here. But in the even layered case, the hinge state position changes, and it indeed, say, reproduces this theoretical expectation. So this is a final slide. I consider the electrolyte type of material as a topological material, and in particular case of apatite, there's a one-dimensional hinge state. Yeah, and another case is a action insulator, where we find that for even numbered and odd numbered layers, there's a different hinge state configuration. So thank you very much for your kind attention.
Thanks for the wonderful talk. Now the talk is open for discussion. Any questions or comment?
Can I ask a question, Professor Murakami?
Yeah.
Yeah. Hello. How are you doing?
Very good. Yeah, it is nice to meet you here.
Nice meeting you. So thanks for your wonderful talk. It's really insightful. I'm just wondering that how would this hinge states would show up in a quantum Hall experiment?
So yeah, in a quantum it is just like a chiral hinge state. So in the 3D, it's like say going around the crystal in a complicated way. But if we make it very thin, then it is really like the say one-dimensional chiral edge state. So suppose we begin from this one, and we make this very thin. Then it is just so it is shown in this way.
Okay.
Yeah, so it's a chiral hinge state, chiral edge state.
Okay. And another question would be that a filling fraction, I mean, 2/3 of a fraction for the vertex, this thing, is there a signature of interactions there? In the sense that could there be some kind of fractional I mean like a I don't know, I mean maybe some like would this again show up in the quantum Hall as a fractional filling and would correspond to some composite fermions and so on? It has an odd denominator.
Yeah, but this is a kind of an electron filling.
Okay,
yeah,
okay.
Yeah, of course, if it is a random level filling, it leads to some kind of interesting behavior of a fractional quantum Hall. So this is the kind of one-dimensional chain.
Okay.
Is a fractional filling.
Okay.
So in that sense, it can undergo a Piles transition, for example.
Yeah. Okay. Okay. And the spins of the electrons do not play a role. Because I mean, is there a skyrmion excitations?
That I do not know. Yeah, here we studied the spinless case because in this particular case, the spin coupling is very small.
Okay.
Yeah, but but it might be an interesting possibility to consider such kind of a spin effect of a spin coupling.
Okay. Thank you very much.
I have a question, Professor Murakami.
Yes.
You said that the low work function of interstitial electrons is good for topological properties.
Yeah.
So why it is so? Why the low work function is required?
Okay, so so in many insulators, typically ionic insulators, electrons are strongly bound to atoms, and it opens a large gap. So in that case, it is very difficult to invert the gap by some other, say, interactions. Yeah, for example, spin-orbit coupling. But in this case, these electrons are very weakly bound to, say, in this case, it's very weakly bound to the atoms. So they tend to have a smaller gap.
Okay.
Or they can be controlled easily by external parameter, external change. Yeah.
Okay. Okay. Thank you.
Any other question? If not, I think the time is up. So let's thank all the speakers in this session and close this session.
Yeah, thank you, Professor Uchida and all the three speakers for this session. The next session will start in about 10 minutes of time. And I would like to request the chairperson, Professor Saurabh Basu, to take care of the next session, which will start at local time 11 a.m.
Yes, I'll do that.
Thank you.
Okay, should we start?
Yeah, maybe we can start. Yes.
So welcome to the second scientific session. It has two talks, and the title of the session is Quantum Transport in Condensed Matter. And the two speakers are Professor Akihisa Koga and Professor Masaki Uchida. So I invite Professor Koga to start speaking. Is the title of the talk is Majorana mediated spin transport in Kitaev quantum spin liquids. Professor Koga.
Thank you very much. So first of all, I would like to express sincere thanks to organizers for giving me an opportunity to talk in this workshop. I would like to talk about Majorana-mediated spin transport in the Kitaev spin liquids. My name is Akihisa Koga from Tokyo Institute of Technology, and our collaborator I like this. The main player is Minaga-san. He was a master course student in our group. Now, so we focus on the transport properties. We consider the certain circuit with a battery. The electron go around in the circuit, and the electric current flowed in this direction. In this case, electrons are needed for the electric current. But in general, electrons are not needed for the electric current. So Maxwell's displacement current is described by the differential of the electric field. Therefore, in that case, the electrons plays no role for this current. So therefore, electrons are not needed for the electric current in general. How about spintronics? Recently, spintronics has attracted much attention, and in the spin current is mediated by the magnon in the conventional magnet and the spinon in the one-dimensional Heisenberg chain. So magnons and the spinon have a spin, so therefore spin current is flows with spin fluctuation in the system. My question is spin current without spin moment possible or not? Like a displacement current in the electronics. Now, to this end, we focus on the Kitaev model. Kitaev physics has attracted much attention since the candidate materials has been synthesized, such as sodium iridate and alpha ruthenium chloride. One of the interesting phenomena in this field is the half quantized plateau in the thermal quantum Hall effect observed in the alpha ruthenium chloride, which stimulate further investigations on the fractionalization in this system. So Kitaev model is one of the two-dimensional quantum spin model on the honeycomb lattice. Model Hamiltonian is like this. Hamiltonian is composed of the Ising interaction in the x direction and y direction and the z direction, so-called x bond, y bond, z bond. In the x bond, spins two spins tend to be parallel in the x direction, y bond is the y direction, z bond is the z direction. Therefore, this induces a bond frustration in the system, which suppresses magnetic long-range order. One of the important points in this model is the existence of the local conserved quantity. The corresponding operator WP is like this. Product of the 6 kind of Pauli matrices, the number is like this bracket. So WP square is unity because the square of the Pauli matrices is unity. Also, WP commute with Hamiltonian, also commute with the other bracket operator Q. So therefore, in this system, each eigenstate is belong to the subspace specified by the set of the WP. WP is the eigenvalues of the WP, like this. According to the Lip's theorem, the ground state belongs to the subspace with WP's unity. Then we can discuss interesting ground state properties. Before discussion, we little bit consider the commutation relations of the WP. So WP is like this. This is defined by the 6 kind of Pauli matrices. So WP includes sigma 1x. So therefore, WP and sigma 1x commute with each other. On the other hand, sigma 1y and sigma 1z, so anti-commutation relations, because there are anti-commutation relations between the Pauli matrices. Then we consider this equation, WP times sigma 1y times ground state. So due to the anti-commutative relations between WP and sigma 1y, so minus sign appears around here, and WP is unity for the ground state. Therefore, we obtain this equation. Then we found that sigma 1y times ground state has a -1 eigenvalues of the WP. This is schematically shown like this. This is the eigenvalue of the WP. So if you put put the sigma x on the side 1, so due to the commutation relation, the eigenvalues of WP is not changed, but the sigma y and the sigma z, due to the anti-commutative relations, eigenvalues of WP is flipped. Then we can discuss interesting ground state properties. If you consider the sigma I x times ground state, 2 of brackets, eigenvalues of WP is flipped. Sigma jx is like this. So as you see that the configuration of the WP is completely different from each other. Therefore, inner product of the inner product of these two states, so-called the spin-spin correlation, is exactly 0. So therefore, we can say that the no long-range order appeared in this Kitaev model. So-called the quantum spin liquid state is realized. Quantum spin liquid state is realized. As for the excitation, so a little bit complicated, but by means of the Jordan-Wigner transformation and also Majorana representation, we obtain the Hamiltonian like this. This C is a Majorana operator. Majorana operator is a creation and annihilation operator is the same. So therefore, this term is just a free hopping term. Also, this is a free hopping term. A little bit correlated hopping term, but eta is related to the local conserved quantity shown in the previous slide. So if you consider the ground state, WP is unity, in that case, the eta equal unity. So therefore, you can neglect this eta R, then the Hamiltonian is just tight binding model. We can easy to diagonalize the Hamiltonian, then we obtain the dispersion relations. So famous Dirac cone appears in the dispersion relations in the K point, at the K point and the K prime point. So important point in this Kitaev model is the spin fractionalization occur. Spin fractionalization means that the spin degrees of freedom is divided into 2. So this WP, so-called the localized Majorana fermion and free hopping itinerant Majorana fermions. Spin degrees of freedom is divided into 2. This is a spin fractionalization. So in this model, so what happens in the spin transport? This is my question. So already, so Majorana edge current has been observed in the alpha ruthenium chloride, but now, up to now, we don't know the bulk transport property in the Kitaev system. Now, we would like to discuss the spin transport in the Kitaev model. First of all, we a little bit prove some equations. The important point in the Kitaev model is no spin moment and no spin correlation appears because the quantum spin liquid state is realized. Now we prove this equation. So ground state sigma ix times ground state. So ground state has one
eigenvalue of the WP. So therefore, introducing WP is easy. Then the WP and sigma IX sometimes has a anti-commutation relation. Therefore, minus sign appears around here. The WP is -1 eigenvalue of the eigenvalue for the ground state. Then we obtained like this. So therefore, we can prove the absence of the magnetic moment. So important point, this equation is the existence of the WP. In the honeycomb lattice, two of bracket has anti-commutative relations between the WP and the sigma IX. But if not, what happens? For example, where in this line, so therefore some edge or defect, or if the magnetic field is introduced, so this WP is no longer a local conserved quantity. So what happened in that case? Now we would like to discuss the such cases. So we consider this setup. This is a no magnetic field region, and this is a yellow and purple region. In that case, the weak magnetic field is introduced. So if no magnetic moment is applied, so spin moment never appear. But if you introduce the magnetic moment, we could not prove the absence of the magnetic moment. In general, so finite magnetization appears in this area. Next, we consider the spin-spin correlations. Yellow and white region, we can prove the absence of the spin-spin correlations because there is a local conserved quantity in the middle region. Purple and white region is the same. However, we could not prove the absence of the spin-spin correlation between the yellow and purple region because there is no local conserved quantity in the colored region. So it is possible or not. So to clarify this, we consider the real-time dynamics in the Kitaifu model. So setup is here. In the middle region, there is no magnetic field, and the left and the right region, we introduce the small magnetic field. Now we introduce the magnetic pulse in the left edge region. What happens? So to clarify this, we make use of the Mariner mean field theory like this. So this is this is one of the mean field theory, but if magnetic moment is 0, this Mariner mean field theory reproduces the exact result because this is a correlation term, but gamma bar is a local conserved quantity. Therefore, in that case, this Mariner mean field theory reproduces the exact result. So therefore, we can believe that if the magnetic field is weak enough, this Mariner mean field theory reproduces the correct result. To check our result, we also may perform the exact diagonalization with the 24 side. Later, we will show some result. So now we consider this setup, then we introduce the magnetic pulse in the left edge. What happens? So this is a setup. So yellow region is here, and the middle region is here, and this is a purple region. Now we introduce the magnetic pulse in the left edge. What happens? So this is a change in the magnetic moment. As I said, the weak magnetic field is already introduced. Therefore, in the yellow and purple region, there is a finite magnetization. But now we focus on the change in the spin moment. This is the animation of this real-time dynamics. You can see that some fluctuation appeared in the left region and the right region, but never no fluctuations appeared in the middle region. Like this. So in the middle region, never never fluctuated, but the light region, after some delay, we found some fluctuations appeared in this light region. So what happens in this system? So we make use of the minor mean field theory. So therefore, we can also calculate the itinerant minor mean field and the localized minor mean field. So we found that the spin moment never appeared, but localized minor fermions never appeared, but itinerant minor fermions fluctuated even in the middle region. So therefore, we can say that this spin fluctuation flows mediated by the itinerant minor fermions. So this is it's not animation, so static figure. This is a time evolution, and this axis is a distance from the left edge. So at t equals 0, we introduce a magnetic pulse. Therefore, in this left edge region, some fluctuations appeared around here. In the middle region, no fluctuation appeared in the spin moment and the localized minor fermions, but we found some fluctuation in the itinerant minor fermions. In the right region, you can find that some fluctuations appeared in spin moment. The localized minor fermion, it's essentially the same. So, so in the middle region, we could not find any fluctuations. Therefore, we can say that the spinless spin transport was observed. So this phenomena can be explained easily. So SG is described by the product of the localized minor fermions and itinerant minor fermions. Therefore, introducing the magnetic pulse in the left region, the localized and itinerant minor fermions both excited. In the middle region, due to the spin fractionalization, localized minor fermions and itinerant minor fermions are completely decoupled. So therefore, only itinerant minor fermions float. In the light region, already we have applied the magnetic field. So therefore, weak hybridization between the localized and itinerant minor fermions, then we found that the spin fluctuations in the light region. So we could find such a spin transport in the Kitaev system. So in the realistic system, we have to consider the stability of this spin transport. So in the realistic system, for example, the iridate and the alpha ruthenium chloride, there are not only the Kitaev term, but the Heisenberg term and the gamma term. If the Heisenberg term and the gamma term exist, the WP is no longer local conserved quantity. So therefore, what happens for the Majorana mediated spin transport? To clarify this, we consider the same problem by means of the exact diagonalization method, because WP is no longer the local conserved quantity. 24th side is like this. So left side is only 3 side and the right side is 6 side. But very small system, but we found that some placket in the middle region. So important point is that there is a local conserved quantity in the middle region. Then the spin transport property characteristic of the Kitaev system can be captured. So this is a result for the no Heisenberg term case. So this is the distance from the left edge. This is the time evolution. The left region, you find that some fluctuations appeared. Of course, we introduced the magnetic pulse. In the middle region, there are no spin moment appears around here, but we find the light region, some spin fluctuations appears. So this is the Majorana mediated spin transport, then which is completely consistent with the previous slides. Now we introduce the Heisenberg term, weak Heisenberg term like this, 0.03. So this is a distance from the left edge. This is time evolution. You can find that some fluctuations appear in the light region. It is essentially the same as the left hip figure. Therefore, we can say that the Majorana mediated spin transport still survive even in the as long as the Heisenberg interaction is small enough. So around here, you can find that some fluctuation appears in the spin moment. This is due to the proximity effect around here. So in that sense, this is some very tiny spin fluctuations appeared around here, but this is just tunneling effect. So we also consider the anisotropy of the Ising interactions. Originally, Kitaev discussed this model. So X bond JX, Y bond JY, Z bond JZ. Up to now, we have discussed only isotropic case, JX equal JY equal JZ equal unity. In that case, the system is gapless. Then we can find that Majorana mediated spin transport. But if you consider the anisotropy, so gapless spin liquid state go to the gapped spin liquid state. What happens in this direction? So this is the dispersion relation. This is the dispersion relations of the isotropic case. You can find that the Dirac cone appears around here. If you introduce the anisotropy, Dirac cone is shift disappears. In that case, gapped behavior appears. Now we focus on the effect of the anisotropy. So this is the result. This is the left edge and the right edge. Similar simulation we performed. So introducing the this is the isotropic case and the anisotropic case. JY is 1.5. So this is the dispersion relations. So now we focus on the X direction. This velocity in X direction is described by like this. Square root of 3/4 times JY. So therefore, introducing the anisotropy in the JY, then the velocity of the Majorana mediated spin transport. So this is distance from the left edge. This is the time evolution. So this black line is V square root of 3/4 times 1, and this is times 1.5. So you can find that spin fluctuation appeared above this red line. This is 1.5. So this is consistent with JY. So therefore, we can say that we confirm that Majorana mediated spin transport occur in this system. So what happens is the gapped state. In the gapped state, we could not find anything in the spin moment. However, if you consider the rescaled plot, some fluctuations appeared in the light region. Of course, in the middle region, we could not find anything, but the light region, some tiny fluctuations appeared in the spin moment. This is due to the tunneling effect. So in the middle region, so gapped region, but finite width. So therefore, tunneling effect occur, then we can find some tiny fluctuations in the spin moment. So we confirm that Majorana mediated spin transport occurred in the system. Let me summarize my talk. We have discussed the Kitaev model to discuss the transport properties. by means of the Majorana mean field theory and exact diagonalization, we found that Majorana mediated spin transport. So this is a contrast to the Majorana edge current observed in the alpha ruthenium chloride. In the alpha ruthenium chloride, so this edge current is observed originate from the topological nature of the honeycomb sheet. So this is just the edge current, but we found Majorana mediated spin transport is bulk properties. So therefore, we expect that such a bulk transport will be experimentally observed in the near future. Thank you for your attention.
Thank you very much, Professor Koga. It's an excellent talk. In fact, really enjoyed listening to it. Can you hear me?
Yep.
Okay. So time for some questions, comments from the audience. Any question? Professor Koga, I'll ask a question. Since in the spintronic materials, ordinary spintronic materials, there's a strong requirement of a spin orbit coupling. What would be the analog of the spin orbit coupling in a Majorana mediated spin transport?
This is just a toy model, of course, but if most important candidate material alpha ruthenium chloride, the spin orbit coupling is quite large. The effective model is this type model in that system. So in that case, so this is not a real electron spin.
Yeah, so maybe the your JH and all these the Heisenberg couplings can be tuned, which would play the same role as your spin orbit coupling, because that's how you'd get larger spin current.
To get a large spin current?
Yeah. Like if I see it as a tunable quantity, what would be what would you be tuning in, say, an experiment on, say, alpha ruthenium chloride?
Sorry, I didn't consider. So probably no experiments observed such a Majorana mediated spin transport. So one of the possible candidates is thin film of the alpha ruthenium chloride, but no experiments succeeded. So therefore, I cannot answer that question. Sorry.
No problem at all. Is there another question that we could take before we close down? All right, then if there are no questions, let's thank the speaker. It's an excellent talk. I really enjoyed, as I said earlier also, I really enjoyed listening to this. Thank you very much.
Thank you very much.
All right, so we are in the second scientific session, and I would, this is Saurabh Basu here from IIT Guwahati. I would request Professor Masaki Uchida to talk about quantized transport in topological semi-metal films. Over to you, Professor Koga. Professor Uchida.
Can you hear me?
Yes.
Thank you, Chair, for the kind introduction. I'm Masaki Uchida from Tokyo Institute of Technology. First of all, I'd like to thank all the organizers for holding such a wonderful joint workshop. So today I'm very happy to introduce our results, especially about the observation of the quantum Hall state in three-dimensional topological symmetrical surfaces. So here are my collaborators. So I have just moved to TokyoTech in this September. And before that, I was in Professor Masashi Kawasaki group in the University of Tokyo as a lecturer. So I particularly acknowledge these three students for film growth and characterization, and also Tokunaga group members at ISSP for high field transport measures. So I'm afraid I repeat the introduction because it has been already nicely introduced by previous speakers. But here I list some types of the three-dimensional topological materials. In the case of topological insulators, the orbital character of the conduction and valence bands are inverted, and the helical Dirac cone surface appears within the gap. Compared to this, in topological symmetry, conduction and valence bands touch at a point and form the three-dimensional Dirac dispersion in bulk. So when the time reversal or space inversion symmetry is broken, the Dirac point or accidental degeneracy of the wire points is resolved and they are separated. For example, these typical materials have been intensively studied as Dirac or wire-same metals. So in particular, the topological Dirac-same metals can be changed to many other topological phases by reducing symmetry or dimensionality. So it is called the parent material. So here I'm more focused on the surface state of topological insulator or same metal. So this is the top view of the surface dispersion in the case of topological insulator. So as you may know, the helical state appears as a full loop. So on the other hand, in topological same metal, the surface state starts from this red wire node with plus chirality and then ends at the blue wire node with the minus chirality. So it is called Fermi arc. So these two wire points seem to be connected, particularly in the case of Dirac same metal, but belong to different chirality. So they are not connected, and the electron cannot complete the magnetic orbit motion on only one surface. So even the Shimikov-Doherty oscillation, which is a kind of interference effect, cannot be expected for such a simple topological same metal surface. So there's a trick, and actually this is one of the most important features of the topological same metal. As you may know, in the case of the parabolic or two-dimensional Dirac dispersion, the random levels under the magnetic field can be expressed as shown here. In the case of three-dimensional bulk Dirac dispersion, this additional term, k dot n square, is added to the original two-dimensional equation. So particularly when the index n is 0, the equation shows momentum linear dispersion along the field direction, and which is called the chiral zero mode. So this mode is indeed a source of the unique magnet transport proposed for topological same metal, such as chiral anomaly. And actually, the electron on the topological same metal surface can complete the magnetic orbit motion by using this mode, as I discussed later. So in recent years, many topological same metals have been theoretically proposed and also experimentally confirmed. Among them, the cadmium arsenide and sodium-3 bismuth are typical Dirac same metals hosting the simple bands. So they have only two bands forming Dirac dispersions over a wide range of energy. In particular, the cadmium arsenide shows very high mobility and long mean free path, almost isotropically. So in addition, the chemically stable 112 plane is not perpendicular to the 001 Dirac node direction. So these features are very favorable for investigating the quantum transport in topological same metal surfaces. So in terms of the sample preparation or film growth, there are also advantages and disadvantages. The left panel is the surface morphology of cadmium arsenide film taken by AFM, and the right panel is some powdering profile of sodium-3 bismuth film taken by STM. So in the case of sodium-3 bismuth, the Fermi energy is almost on the Dirac point, but this material is very air sensitive and so may not be favorable for device transport measurement. On the other hand, the cadmium arsenide is very chemically stable, but readily vaporizing. So namely, it is difficult to grow thin films due to high vapor pressure. Also, N-type carrier is easily induced by arsenic deficiency. So it is important to overcome these 2 points in the cadmium arsenide study. So to solve the vapor pressure issue, we took an original approach using solid phase epitaxy. So by optimizing the capping layers and also substrate, we have succeeded in realizing very high temperature crystallization, where the cadmium arsenide vapor pressure reaches as high as 10 torr. So as shown in TM image of an obtained film, you can confirm the clear atomic arrangement without any discernible defect. So actually, this film crystallinity is much better than the bulk one. So typical rotting curve width measured in the X-ray diffraction is only 1/4 of the bulk one. So we also found that this technique is good at controlling the thickness very accurately, which is also crucially important for growth of the Dirac metal film. So by measuring these high quality films, we have first reported a quantum Hall effect in cadmium arsenide films. So you can clearly confirm the zero resistance and the quantized plateau in R by X. So interestingly, the degeneracy is different between these 2 films with different thickness. By measuring detailed thickness dependence, we find that the spin degeneracy or G factor largely changes depending on the confinement gap size, so which is very sensitive to the confinement thickness in the Dirac dispersion with high film velocity. So namely, the fast Dirac dispersion results in the thickness-dependent quantum Hall states and topological transition. So thickness and dimensionality are very important in the Dirac metal films, and topological transition can be induced also by such a dimensional change. So here is the field angle dependence of the Shimnikov-Doherty oscillation observed for various thickness fields. So in the 23 or 37 nanometer film, the oscillation peaks and valleys show shift with rotation of the magnetic field angle, and eventually disappear for 90 degrees in plane field configuration. So which indicates that the 2-dimensional Fermi surface is realized in such a thickness. So quantum Hall effect shown in the previous slide corresponds to such a confinement region. On the other hand, peak and valley position do not shift to 90 degrees in a rather thick film, 100 nanometer film, indicating that the 3-dimensional Dirac metal phase is realized at this thickness. So in addition, we have developed doping and gating techniques to reduce the N-type carriers in cadmium arsenide. So by combining the zinc doping and backgating through the strontium titanate substrate, we can even reach the P-type region after a large increase of RXX at the charge neutrality point. By making such a fun plot based on the gating experiment, we have also succeeded in clarifying the detailed subband structures of the 3-dimensional Dirac dispersion. So then we have succeeded in observing the surface conduction and its quantization. Here I compare 2 quantum Hall states appearing for different thicknesses. In the case of 35 nanometer film, the bulk oscillations, as indicated by an open circle, are not observed in the in-plane configuration. So again, the two-dimensional Fermi surface is realized. On the other hand, in the case of 100 nanometer film, oscillations as indicated by an open circle can be observed still in the in-plane configuration. So the three-dimensional Dirac metal phase is actually realized at this thickness. In this case, at higher fields, we can find other oscillations with different frequency together with the whole plateau structures as indicated by a red square. So these features are not observed in the in-plane field configuration. So this can be interpreted to some two-dimensional state appearing in the three-dimensional Dirac metal phase, and possibly so-called wild orbit state mediated by the chiral zero. As one of the evidence, here I present the temperature dependence of the oscillation. So the fine oscillations, as indicated by a red square, almost disappear at about 50 Kelvin, but the bulk oscillations originating in the fast Dirac dispersion remains up to 200 Kelvin. So the obtained effective mass is totally different between the surface and bulk states. And the surface one is much larger than the bulk one, so reflecting the theoretically calculated band structure. So zinc doping dependence is other clear evidence. So as zinc is located above cadmium in the periodic table, its spin-orbit coupling is much weaker than cadmium. So by doping zinc, the system becomes a trivial semiconductor above the critical composition of about 0.19. So again, the fine surface oscillations are observed only for the out-of-plane field configuration, which is more clearly seen in the plot for the inverse of the magnetic field. So above the critical composition, only the surface oscillations disappear and the bulk oscillations still remain. So this is a very strong evidence of the intrinsic surface state. So now it is clear that the two-dimensional surface state is observed for topological symmetry, but we cannot conclude its type at this time. So namely, some possible surface orbit types have been proposed. So one is the tunneling while orbit, as I introduced. So where the breaking of the time reversal symmetry by magnetic field may be dominant, and the edge state appears on one edge of the top surface and other edge of the bottom surface. So on the other hand, possibility of the topological insulator like surface orbit cannot be excluded so far. So where the edge state independently appears on top and bottom surfaces. So to distinguish these two states, we focus on the dual gate experiments. So actually many experiments have been performed for topological insulator case. So in this case, the top and bottom carrier densities are different and can be independently modulated by top and bottom gate, so resulting in such a checkerboard pattern in Hall conductance map for top and bottom gate voltage. Actually, a simple model of top and bottom gate modulation have been proposed by considering the independent chemical potential and capacitance, and also corresponding the surface quantum Hall states have been experimentally observed. So then this type of checkerboard pattern has been demonstrated in higher quality topological insulator films. So in enough thick films, in the case of topological insulator, the square shape checkerboard pattern appears on this map. And another important point is that in the case of topological insulator, the square shape changes into a diamond-like shape with decrease of the thickness, which corresponds to the increase of the off-diagonal capacitance component, but the topology of the checkerboard-like pattern remains independent of thickness. On the other hand, in the case of wire orbit connecting the top and bottom surfaces by chiral zero mode, the top and bottom carrier densities are common and modulated similarly by top and bottom gate, resulting in such a stripe pattern in the whole conductance. The right panel is the experimental mapping obtained for thick enough cadmium arsenide film, clearly showing the stripe pattern. So this strongly indicates that the surface conduction and its quantization occurs based on such a wire orbit. For further investigation of the surface quantum Hall state, we think the molecular beam epitaxy films are very important. So here is the mobility versus carrier density map. The previous films grown by solid phase epitaxy have very high crystallinity and mobility, but the carrier density was rather low compared to other films. But recently, we have succeeded in growing the high quality films with low carrier density and high mobility by MB, and similar surface quantum Hall features have been observed in 120 nanometer thick films. So heterostructures based on the MB grown films will be important in further advancing studies. So in the rest of time, I'd like to talk about our trying to induce magnetization in the cadmium arsenide films. So actually, based on a minimal model composed only of the pair of the wire nodes, so unique transport and spintronic functions such as semi-quantized anomalous Hall effect and voltage-induced spin torque generation have been theoretically proposed. So here, distance between the split wire nodes are very important and simply characterize the non-trivial coupling between the charge and the magnetization, as well as the intrinsic anomalous Hall conductivity. So cadmium arsenide has a very simple band structure, so it may be suitable for demonstrating these wire node-based spintronic functions. So if the magnetization can be successfully induced. So we focus on the magnetic proximity effect and prepare such a heterostructure by growing cadmium arsenide film on a rare iron garnet substrate with strong perpendicular magnetization. So here are anomalous Hall resistance and magnetization curves measured at various temperatures. So in line with the magnetization of the substrate, a clear anomalous Hall effect is detected with magnetic hysteresis. So the saturation once vanishes at about 130 Kelvin, which corresponds to the magnetic compensation temperature of the garnet substrate, but recovers and remains up to 400 Kelvin. So an above room temperature ferromagnetic state is robustly realized using such a magnetic proximity effect. So under the magnetic proximity effect, the Dirac nodes are expected to be separated into a pair of the wire nodes with opposite chirality at a distance of 2 kW along the K112 direction in this case. The observed anomalous Hall conductivity is opposite in sign to the magnetization, and its amplitude increases with lowering the Fermi level towards the Dirac node energy, and also shows a substantially large Hall angles of about 0.1. So all these observations are very consistent with the picture of the simple wire node separation. So to confirm this, we have performed theoretical calculations based on the first principles electronic structure. So in cadmium arsenide, there exists only 2 bands over a wide range of the energy around the Dirac node, and which is separated to the wire nodes by introducing the exchange coupling. So calculated frame level dependence of the intrinsic anomalous Hall conductivity is more or less similar to the minimal model one, and also consistent with the observed dependence. So the simple wire node system has been demonstrated by fabricating the heterostructure of Dirac same metal and ferromagnetic insulator for the first time. So here, take message of my presentation. So cadmium arsenide films with high crystallinity, flatness, and controllability, such as doping and gating, are very useful for systematically studying the quantum transport in topological same metals. So one typical example is the surface quantum Hall effect observed in rather thick films. So this indicates a new quantum Hall state based on the three-dimensional Dirac dispersion and the magnetic field, and which is distinct from the topological insulator surface one. So for further investigating the wire node-based transport phenomena and also spintronic functions, the heterostructure will be a good platform. Thank you for your attention.
Thank you, Professor Uchida. This is a very nice talk. I mean, lots of nice experiments are coming up. So it's really nice to see all these things. Can we have some questions from the audience? Any question or comment? So Uchida, you have shown, so this is of course three-dimensional quantum Hall effects that you are talking about, or other quantum Hall effect in 3 dimensions. In 2 dimensions, it is well known that apart from a plateau at half, you don't have any plateau at any even integer in the denominator. But here you have shown integers, I mean fractions such as 1/4, 1/14, 1/12, etc. So they would not be, either in the Laughlin wave function or in the Chern wave function. They will not be allowed. So can you comment on that? I don't know much about three-dimensional Hall effect.
So in theoretically, even this three-dimensional Dirac dispersion case, there are some non-standard or 1/2 n plus 1/2 state is expected to appear. And experimentally, so far it is a bit difficult to distinguish these two states because quantum Hall plateau is not so clearly observed. But in our dual gate modulations, from our dual gate experiments, it is better to use the plus 1/2 fitting. By using such a fitting, it is better to simulate the experimental results.
Okay. So these even denominators are possibly coming from this plus 1/2. Of course, you have also.
Yeah, that's right. Yeah.
Oh, okay. Thank you. Any other question, comment? So if not, let us thank Professor Uchida for a very insightful talk. Thank you very much.
Thank you.
So we close this session after 2 very illuminating talks, and we move on to, in another about 10 minutes, we'll move on to the third session or the last session of the day. Thank you very much to all of you.
Yeah, thank you. So Professor BP Das will be chairing the final session of today.
Yeah.
So thank you, Professor Basu, and both the speakers.
Thank you.
Perhaps the speakers in the next session could test the slide sharing if you're ready.
Yeah, certainly they can. If they are here, Professor Pankaj Mishra, Professor Girish Setlur, and then today is Mr. Hawasi. All three of you can actually test your slide sharing if you want to.
Okay, so can you hear me, Professor Ghosh? Okay.
Yes, yes.
Yeah, okay.
Loud and clear.
Okay, good. Okay. Yeah, so this. So should we, okay, what, so we've got 10 more minutes, right? Okay.
No, it's going to start now, I think.
Oh.
No, I think we have 10 more minutes.
Oh, 10 more minutes, right? Yeah.
Yeah, okay.
Okay, we have 10 more minutes, yes.
Okay, fine. Okay.
Yeah, it was supposed to end.
Yeah. Okay.
Professor Ghosh, your microphone is still on.
Yeah. Yeah, thank you.
So Professor Das, glad to know that you're relocating back to India and you'll be joining in Kolkata.
Meeting that, sure. Meeting aram ho. It is sound into Mahala. Should be no sound. Nani?
Professor Kuze, you there?
Yes, yes.
How would we take the conference photograph? What do you
We just take a screenshot what you are seeing.
Okay, so for that time, all the participants will turn on their video.
Yes, yes, that's encouraged.
And then one can take a screenshot, right?
Yes, yes.
And that screenshot can be taken from at your end, I mean, using the Zoom?
Yes, yes. From my computer, I will take a screenshot.
Okay, all right. Okay, thank you.
So Professor Das, you're now
Yes,
back.
yes. Okay, so yeah, so just 2 minutes, right? So we'll start in, okay, 2 minutes. So you can hear me?
Yeah, I can hear you, yes.
Okay, good. Okay, so let me welcome you all to this session on dynamics of bosonic systems. And so we'll start now. The first speaker is Dr. Pankaj Mishra. So you have, 25 plus 5.
So thank you, Professor Das, for giving me an opportunity to talk my work. And also I thank organizers for giving the opportunity. So today I'll be talking about two aspects of superfluid turbulence. One is the dynamics of quantized vortices, which is supposed to be the lifeline of this turbulence. And another one is the energy spectrum, and it gives us the statistical idea that how the energy get transferred from one scale to another scale in superfluid turbulence. So before starting my talk, I would just like to show one animation, and through that I would like to begin the talk. And in that animation, what we see that these are the quantized vortices, and they come closer to each other, and then they get reconnected, and they get breakdown in between of those structure, and then there is some dynamics associated with that. And finally, at the steady state, what we will find that they become entangled with each other, and we get the turbulence state. So we are basically interested to first know that how this steady state being reached to the system, and what are the dynamics associated with this quantum vortices. And then we'll be interested to know that how the energy, suppose we supply some energy to the system, how the energy reached to this the vortices. So with this, I again switch to my slide and start the talk. So this is the outline about today's talk. First, I'll introduce about this quantized vortices in superfluidity. Then I'll be talking some of the experiments that we are trying to understand, and this endeavor is for 4 and 5 years. And then I'll basically talk about not very recent, but 3 and 4 years back our effort when we tried to modify one of the proposition given by Joy Winan, which is supposed to be the pioneer of this quantum turbulence field. And further, I'll talk about some further numerical endeavor in this field. And then I'll talk about the recent work that is related with the energy spectrum in this turbulence superfluid. So here I show you the phase diagram for the helium. So when this helium is cooled below this lambda transition temperature, which is 2.1 Kelvin, then it enters to the phase which is also known as helium-2 phase. And in this phase, it can be considered as the intimate mixture of the two kind of component. One is superfluid component, and another one is normal component. So superfluid component have the zero viscosity, while the normal component have some finite viscosity. So what happens below this lambda transition temperature, the fraction of the superfluid component increases, and as temperature is decreased, it keeps on increasing. At 1 Kelvin, we can see that system is fully occupied by the superfluid component. So below 1 Kelvin, we can consider the superfluid is having only superfluid component, so it will have completely zero viscosity. But what happens in this range? When it has the presence of both normal and superfluid component, then the things become quite interesting, and we are interested basically in this region. So just to give you some brief outline about the quantum nature of the fluid, that how quantum nature appears into the fluid, that we know that for every particle there is a wave nature associated with, and the wavelength of that particle is inversely proportional to the temperature. So as we decrease the temperature, then at certain temperature the wavelength of the particle becomes of the order of the interparticle separation, and then we have the quantum nature of the fluid starts appearing, and we get this Bose-Einstein kind of condensation into the system. So we are mainly talking about the state when we can represent this whole system by a microscopic wave, and the velocity of the system can be given by the gradient of the phase of that wave. So through this relation, what we see that at any point, this system will not have any circulation, because this it is the divergent P the wave function, so it will not have any circulation. But what happens that when we rotate the system and beyond a threshold value of certain angular velocity, there is a local circulation starts appearing to the system, also known as topological defect. And the nature of the local defect has the behavior that at the center of this circulation, the density goes to 0, and the phase has the discontinuity. Also, we can another way we can say that it will be infinite. The velocity of the system will be quite infinite at this core of this topological defect. And this vortex, the circulation is quantized, and it is proportional to this number kappa, which is inversely proportional to the mass of the atom associated with this system. And generally for superfluid helium, this n is 1. So whenever we will talking about, we'll have to keep in mind that circulation of the superfluid helium is constant, which is kappa. So this I am just showing you the steady state behavior of the animation that I showed you. So here you can see the quite turbulent state, or in the other way we can say that vortex tangle are quite entangled to each other, and there are some distribution associated with at the boundaries and in the bulk, and so we'll be quantifying this aspect more as we go along in this talk. So the main motivation comes from very old experiment done by Hall and Wiener in 1956. And what they did, they considered this superfluid helium below lambda transition temperature, and they heat it with the wire, and the fluid is contained in the circular pipe. So what happens that since normal component has the entropy, so it will respond to that heating, and this part is a cold helium bar. So this will respond to the temperature gradient, and normal component will start flowing along the temperature gradient direction. To conserve the mass, superfluid component will start flowing in the opposite direction. So what we see that there is some counter velocity appears into the system, and that generates some sort of mutual friction, and that was the responsible for the turbulence behavior in the system. So what was it being observed at finite temperature and what below lambda transition temperature, there was a state in which superfluid component becomes turbulent. So we'll get the entangled state of this quantized vortices, but the normal component, which we can also assume at the non-condensate part of the system, that basically has the laminar in nature. It is not turbulent, but there is another state called T2 state in which both components become turbulent. And you can see that the experiment was done 1956, but that time technologically it was not so advanced, so there was no direct observation of the behavior of a normalized superfluid component. So recently it has been observed through this recent advancement in the technology. So what they observed that when a normal component remains laminar, then it has this parabolic profile. So what we see that at the boundary, this component is 0, but in the bulk of the system, this system will have the maximum velocity, maximum mean velocity. But as we further go to the transition to the next state where both normal and superfluid component become turbulent, then what we find that there is some flattening happens near the wall, and further in the T2 state when both components are turbulent, what we realize that there is very complicated state. So there are a lot of efforts going on from the numerical front to understand this behavior, and still we don't have the success in this front. So here the another issue is that due to this presence of the wall of this container, there is inhomogeneity that being added to the system, and that also creates some difficulty in understanding the problem, and we'll basically we have got some success in getting this thing into account. So the another aspect that I would like to highlight here, the energy cascade behavior in quantum turbulence. So what we basically find in the classical turbulence, that suppose if we apply the force at a particular scale, so suppose at large scale, then the system becomes the motion start to the system, and then what we realize that at very small scale there is diffusion, and the energy basically get transferred from large scale to a small scale through some through the nonlinear interaction, and finally it get dissipated at very small scale. So this particular thing was quantified by Kolmogorov in 1941 for classical turbulence, and it is being told as the energy density. So here I have shown you the relation that this is the energy in the Fourier space of the system. So if you consider all the energy in the Fourier space, that we get the total kinetic energy. So this is known as the energy density. So what we realize that energy density in this range, which is also known as inertial range, is independent of forcing as well as the viscosity of system. It only depends upon the particular scale, and it has this behavior with the scale. K here is the wave number which is inversely proportional to the length scale. So it behaves like k to the power minus 5/3 power law. And here I have just represented the cascade picture of the energy. So suppose I give the energy to the big eddies, then it breaks down as we lower the scale, and it further breaks down into the many parts, and it keeps on continuing once it reaches to the dissipation scale, where the energy gets dissipated due to the heat. So this is the scenario for the classical turbulence. But in quantum turbulence, we have the presence of superfluid as well as classical fluid as the normal component. So here another thing is that we don't have any sort of viscous dissipation for superfluid component at a small scale. So in this case, what happens that at large scale, interestingly, it behaves same like a classical fluid, but as we go to the smaller scale, then you can see that there is some cascade happens, but cascade happens due to the Kelvin wave instability. So at large scale, cascade is due to the eddies, but a small scale cascade is due to the Kelvin wave instability. And further, at very small scale, this is not known quietly, but at very small scale, the energy gets dissipated due to the phonon emission. So I'll be basically talking about this part also that we have tried to understand through our numerical simulation. So there are various models in this field. First one is the Gross-Pitarski model, but that is only valid for t equal to 0. Second one is the two-fluid model proposed by Landau and Sija to describe superfluidity at finite temperature. Here we see some modification into that to take into account of turbulence behavior. And then another one is the vortex filament model. So I'll be mainly talking about two-fluid model and the vortex filament model. So here I just given the Gross-Pitarski model. In that the model is given for the macroscopic wave function, and further we can show that this model in the continuum limit can be written as a Euler equation. So at very large length scale, what we find that we can have the continuum model like normal fluid kind of model, in which the equation for the superfluid component and the normal fluid component can be represented by the dynamical equation. So for superfluid component, since it didn't have any viscosity at large length scale, so we can represent it like a Euler equation in absence of any viscous term, and the normal component equation can be represented like just like a Navier-Stokes equation. Only difference would be that presence of this coupling term, and that mainly arises due to the mutual friction between the normal component and superfluid component that we discussed, that arises due to the relative velocity between these two components. So what we see that this mutual friction term is proportional to the relative velocity between the superfluid and non-fluid component. And it is also proportional to this vortex line density, and we'll be talking about more as we go along. So another model is being used in this field is known as vortex filament model, in which we consider the quantized vortices as a one-dimensional filament. And in that case, what we consider that you can see that since the system is incompressible and its circulation is given by omega, which is as a fixed value, so we can use the Biot-Servat kind of equation in order to get this the velocity. So velocity will be given by this relation where the r prime is the point at which we which our vortex point is, and r is the point where we want to find the velocity. So further we can parameterize this vortex using this one-dimensional length, that is zeta, and this particular equation will get converted into this form, where we can see that kappa is coming because kappa is the fixed the vorticity for the superfluid component. Only its orientation can change, and that can be captured through this s prime, which is the derivative of vortex with respect to the arc length. So this then further there was a work by Schwarz who proposed the vortex interaction model, that if suppose two vortex line come together. And so when it comes below a minimum separation, then there will be reconnection between these two, and that will result as an exchange of segment, and it will have this kind of behavior, and further this will keep on happening for all the vortices. And you can see that it adds some sort of curvature to the system, which is also equivalent to having the turbulent behavior into the system. So in order to take into account of the normal component behavior, we can see here that mutual friction can be written as it will be proportional to this relative velocity between the normal component and superfluid component. And then since here what we find, there is circulation and there is relative velocity between the normal component and superfluid component, that will add some Magnus force. And since for a vortex filament, the inertia is 0, so we can balance this force. So dissipation, mutual friction force, and the Magnus force addition will be 0. And then we can get that how the vortex point will move in presence of the normal component. So here we have done some simulation, and what we considered for time being, that normal component dynamics we are not taking into account. We are keeping the normal component as a parabolic profile, like a laminar profile. So it will have the maximum in the middle of the box, and 0 at the wall, and then it will be parabolic profile. So in that case, we only solve this the vortex line the dynamics in presence of this normal component. And we consider this length of the box, and generally we consider different mean velocity for the normal component. And this particular things have been solved using the Niputta the fourth order equation. Fourth order method, and we have considered various temperature. 1 Kelvin with a situation when we have only presence of superfluid component, 1.6 both components are present, and 1.9 Kelvin just very near to the lambda Tyson temperature. So we expect that only normal component will dominate to the dynamics. So here I show you the steady state behavior of the simulation. So what we find here, that this is the entangled vortex lines that we get into this picture. So what you can see that in the bulk, these vortex lines are really straight. Okay, so that corresponds that this velocity is not changing much in the bulk. But if you go near the wall, then you can see that its curvature. You can see the curvature. It is basically pinned to the wall. So and it has a many twists near the, so many activities are happening near the wall, and here same thing is happening. So to get an idea that what is the configuration of the normal component and superfluid component, also how the vortex lines are behaving all over the box. Here what we are plotting this vortex line density, which is the total vortex length per unit volume of in the container, and we have averaged over this the y, x and g direction. So here I am showing you the mean vortex line density in the y direction. So what we find here, that you can see that there is a maximum vortex line density near the wall. So here the same thing we find, but in the bulk we find that it is almost uniform. So what is being observed here, that whatever vortex being generated near the bulk, it is being pushed near the wall. So there is some dynamics associated even at the steady state. So I'll be talking more about that how can we take into account of the dynamics. If you look at the profile of the normal component and the relative velocity between normal and superfluid component, we find that both profile have this parabolic in nature. So it is maximum near the wall, contrary to the what we get for vortex line density, which is the minimum near the minimum in the bulk. So then in 1957, Winan basically proposed that how can we take into account that what will be the dynamics corresponding to the vortex line density. So he proposed, totally based upon the dimensional analysis, that there are some parameter into the system, that the vortex line density, which has nothing but the dimension of meter per square, and there is a diffusivity of this quantized vortices. So on that basis, he considered that how we can generate the production term behavior, which will be proportional to the L square.
Yeah.
And similarly, he can propose the behavior of the decay term, and that is
So,
also
excuse me, you have 5 minutes.
proportional to the L square. So what we can see here, that on dimensional basis we can construct the various quantity and which can have a different exponent. So to take into account of this inhomogeneity into the system, because we have seen that there is a some gradient of the vortex line density from the bulk to the wall, so there will be some current associated with that. We consider this extra term into our equation, and for that we have we get some modification in the production term as proposed by the Wienen, and in the decaying term as proposed by the Wienen. So I'll not go to the analytical part, I'll directly go to our result here. So what we find here, that this P1 and P2 was the form proposed by Wienen for the production term, and this P3 is the form proposed by us, and this P numerical is the form that we are getting from our numerical simulation. So what we get here, that this production term is maximum in the bulk, while it is minimum near the boundary, but we get a good agreement with the numerical simulation with our proposed value. Similarly, with the decaying term, what we find, that decaying is maximum near the wall, but it is minimum near the bulk, and that we also get good good verification with our numerical simulation. And then we compute the current in the current line, this vortex line density, and what we find, that main current is along the boundary direction. So you can see here it is positive, and the current gradient is also positive in this way. So the vortex is mainly being pushed towards the wall. So on that basis, we propose some modification in the equation. Then further we modified this thing using our the model, in which we take into account of the dynamics of the normal component also, and we find the similar sort of behavior for the vortex line density as well as for the normal component, fluid component the profile. The only thing what we find, that we, as you further go to turbulent state of very high turbulent state, then no fluid component becomes flattened near the wall, which is being verified in the current numerical simulation by Sugota group. They also find flattening of the profile in the bulk of the system. So this is the conclusion of the present study for the dynamics, that we have proposed some dynamical equation for the vortex line density through our numerical simulation and the analytical result. And with this, I just move to the second part, and where we have considered the energy spectrum for superfluid turbulence at below lambda transition temperature. So what is being asked here, that below lambda transition temperature, what we find, that the fraction of normal and superfluid component basically changes below the lambda transition temperature, and at 1 Kelvin we have only superfluid, and near lambda transition temperature we have only normal component. So what being observed in the experiment, that for all the temperature range, the 1.2.3, which is above lambda transition temperature, only normal component is present, Kolmogorov spectrum is seen. Even in the superfluid phase, Kolmogorov spectrum is seen at large scale. So this is very interesting thing, and that we wanted to address. And for that, what we did, that we have not done this direct numerical simulation. We have used this the cell model, in which we model the Navier-Stokes equation into the one-dimensional model, and we preserve the symmetry of the Navier-Stokes equation by using this cell model. So this is a cell model for normal component, and this is a cell model for the superfluid component. And we choose A, B, and C in such a way that symmetry of the Navier-Stokes equation is maintained. And with that basically we perform this simulation using this numerical technique for all the range of temperature. And here I show the energy spectrum for normal component, which is being shown here with a solid line. and for superfluid component is shown here with the dotted line. And this is the normalized spectrum. And what we find that for all the temperature, the spectrum is Kolmogorov-like. So that basically is very much consistent with the experimental observation that we get even with this the simplified model. So other thing that I wanted to discuss about this scale-to-scale energy transfer, in that we have performed that how the mutual friction play important role in order to transfer the energy between these two components. So here just I wanted to show, this is my last slide, that for all the temperature, what we find that mutual friction energy transfer, so this is K, which is inversely proportional to the length scale, we find that mutual friction remains dominant for all the temperatures. So this is blue line is the mutual friction energy. It remains dominant, and that basically very much consistent with the fact that for all the temperature we get the Kolmogorov-like behavior, because mutual friction energy transfer is dominant in the system. So with this, I conclude that in the energy spectrum using the cell model, we have been able to verify the experimental observation that for all the scale and for all the temperature, we get the Kolmogorov-like behavior for superfluid turbulence. So with this, I would like to thank my collaborators. So dynamics part we have done during my postdoc, and some part I did while I joined here. And so I'd like to thank all these people. And energy spectrum part, I have done collaboration with one of the student who came here for 6 months, Avirup Bhadra. Now he's in PhD in the mechanical engineering at TU Delft. And currently I'm also involved in turbulence behavior in BEC system. So with this, I would like to thank for your kind attendance.
Thank you very much for a very nice talk. Now, the audience can ask questions. Yes, questions or comments? Okay. So no questions, no comments. So then, okay, Dr. Mishra, thank you very much for a very nice talk and giving us an idea about your work on superfluid, different kinds of superfluids. So thank you again. So we'll move on to the next talk now, which, okay, so the next talk is by Mr. Hayashi from TokyoTech.
Hello, everyone. Can you hear me?
Yes, we can hear you.
And is it visible?
Yes, it is.
Okay. Hello, everyone. My name is Hayashi. I'm a first bachelor's student and a current member of Professor Van Daar's group. Thank you very much for this opportunity. I'm very honored. Before starting, I'd like to thank Assistant Professor Tapan Mishra and Mr. Sima Mondo, who gave a talk in the session 1 from IIT Guwahati, and of course, Professor Van Der. Thank you very much for many helpful discussions and support. Also, we collaborate with Dr. Da and Dr. Yasuke from Germany. I also appreciate their help and support. Now, let me start my presentation. In this presentation, I would like to share our ideas and the results in the section 3, 4, and 5. Section 3 and 4 are the collaboration works with Professor Mishra and Mr. Mondo. Over the past few decades, quantum phase transitions in optical lattices have become more attractive as quantum technology has improved. Quantum phase transition or phase transitions driven by quantum fluctuations at zero temperature. Optical lattices are arrays of potentials induced by interfering laser beams, and they have high controllability. In 2002, quantum phase transition in an optical lattice was observed. It is the superfluid multi-insulator transition. The Hamiltonian is this, where T is the hopping energy and the U is the on-site interaction energy. And A is a narration operator for bosons, and N is number operator. This is called the Bose-Hubbard model. By varying laser intensities, we can change the ratio U over T and realize a transition. As I mentioned, it is easy to manipulate optical lattices by changing laser configuration. Hence, we can consider double-way optical lattice and three-body constraint. Their feasibilities are referred in reference 3, 4, and 5. Three-body constraint means to restrict the number of bosons on a single site to less than 3. In other words, the cube of annihilation operators on each side is 0. Double optical lattice has a staggered hopping amplitudes as this figure shows. Firstly, we consider a limiting case where U is infinite. In this limit, only a single boson can be on the site. Such property is called hardcore. If the optical lattice is homogeneous and all the sites are filled, then the system indicates multi-insulator phase because of the cost of infinite on-site interaction energy. However, for the case that n is less than L, it indicates superfluid phase. Furthermore, we can find long coherence length in this phase. In double-way optical lattice, a specific phase will arise from n equal L. Similarly, the system is in multi-insulator phase. The specific phase arises at half filling. A boson moves only in an isolated unit, including 2 sites and with T1 hopping amplitude. The bosons cannot straddle over higher wells, hence the coherence length becomes shorter and the gap to phase can arise. The phase diagram is shown in reference 3. The phase is called the bond order phase. For the case that U is finite and attractive, we can also find a characteristic phase, which is similar to the previous one. The existence of attractive on-site energy results in forming pairs of bosons. Thus, the pairs move around. It is a pair superfluid phase. Similarly, in double-way optical lattice, pair bond order phase can arise. Now, we will propose our model. This research is a collaboration with Professor Mishra and Mr. Mondo. In general, bosons interact with each other at long range. For example, Coulomb interaction and the dipole-dipole interaction and so on. Then we consider the case that long-range interactions decay rapidly. In other words, we consider nearest neighbor interactions. We use a suitable variational method, which involves diagonalizing the Hamiltonian to compute the ground state wave function and the energy. It is the DMRG over MPS method. The idea is to truncate the Hilbert space effectively with remaining important states via the density matrices. Let us discuss our model qualitatively. According to reference 7, in homogeneous optical lattice, the existence of such interactions can result in the density wave phase and the super solid phase. For example, at half filling, for repulsive nearest neighbor interactions, density wave can arise. In the phase, bosons are placed on alternate sites like 1, 0, 1, 0, 1, 0, and so on. If a boson is added to the phase, boson can move freely with remaining the density wave order. In other words, the diagonal long-range order and the off-diagonal long-range order coexist. It is the super solid phase. We can infer the dynamics in double optical lattice from previous examples. We consider hardcore bosons for V, repulsive V. For small values of V, we can find the bond order phase at half filling. However, for bigger values of V, the energy cost of bond order phases increases due to this state. Hence, the states are suppressed, then we can find the density wave phase. Actually, we can find the bond order to density wave transition. This phase diagram was obtained from the calculations for the hardcore bosons with lattice size of 200. The states in the outside of blue lines will be the empty state and full state. At rho equals 0.5, in other words, in the inside of the red lines, we can find the bond order to density wave transition. Its critical point is V equal 3.75. Furthermore, we can find the gaps of both phases are connected. For a smaller value of V, for example, taking V equal 1, the density distribution is flat at 0.5 as the left figure shown. Then we can calculate the order parameter for bond order phases, which is hopping energy over a bond. The strong oscillation of the order parameter illustrates a bond order phase. For a larger value of V, we find a density wave phase. To capture the bond order to density wave phase transition, we calculated the structure factor. It can detect the existence of density wave phase. Then we obtain the critical point V equals 3.75. The right figure shows the density distribution for V equal 8. We can find the density wave perfect signature. Our next aim is to investigate phases for other densities, and we will calculate for three-body constraint bosons with repulsive and attractive U. Now, we propose another our research on quantum phase transitions with Dr. Yasuke and Dr. Da from Germany. We would predict quantum phase transitions using machine learning. For our strategy, we use mutual information matrices which has the information of the entanglement of all pairs of sites in the system. The matrix is defined
So
by...
you've got 5 minutes.
Okay. The matrix is defined by two kinds of the von Neumann entropy. I'm attaching an example. As I mentioned, in the standard Bose-Hubbard model, we can find multi-insulator phases and superfluid phases. Then, these two figures determine the mutual information matrices as heat maps. In the rest figure, the off-diagonal components have small values. It means that bosons on a site are not correlated with bosons on the other sites, and it is a multi-insulator phase. In contrast, the right figure shows the mutual information matrix of a superfluid phase. It has non-zero off-diagonal component. Therefore, the mutual information matrices include the information of phases. The first step of our strategy is to combine two mutual information matrices alternately. The combined matrix is labeled same phase or different phase. Then we train our neural network with combined matrices. After training, we put the matrix of another model into the neural network. Then the neural network predicts whether same phase or different phase. Therefore, we can find the phase transitions and estimate its critical point. One of our data sets in the quantum Ising model is the quantum Ising model. We trained with the model with L equals 30 and J equals 1 and J ranging from 0 to 2. This figure shows the training results. The black and red square represent the different phase and same phase respectively. The lower triangular matrix shows correct outcome. The upper triangular matrix shows the test results. The test data points are 20% of the total data points. The prediction matches well. Here, we applied the neural network to the XXZ model. The upper triangle matrix shows the prediction from the neural network trained with quantum Ising model and Bose-Hubbard model. The lower triangle shows correct outcome. Even though the critical point is shifted, the accuracy scored 0.83. However, there exists some room for improvements. Therefore, we will improve our strategy and apply it to our model, which I mentioned before. Let me summarize my talk. In double optical lattice, we can obtain the bond order phase. For three-body constraint bosons, the dynamics of pairs of them arises. Assuming nearest neighbor interactions in double optical lattice, it is possible to find transition from phase driven by the nature of the double lattice to phases by such interactions. And using machine learning methods, it is possible to predict phase transitions. As we saw, by simple assumptions, we can find interesting various phases in optical lattices. Furthermore, we can investigate them by using machine learning idea. That's all. Thank you very much for your attention.
Okay, thank you, Hayashi-kun, for a very nice talk. Any questions?
Hello.
Yes, please. Yes, please ask.
I hope I'm audible.
Yes, yes, yes.
Okay, great. So thanks for a wonderful talk, and it's really nice to see all of you again. Wish we could see each other personally as well. So I recently started getting involved in machine learning. In fact, I've taken a new student now. So I would really appreciate some tips from experts who have more experience than me. So perhaps this is a general request that I would like to interact with you on a more extensive in a more extensive manner later on. But specifically, my question relates to the amount of training data you need, in your simulation. See, typically machine learning is handicapped by the fact that you need enormous amount of training data, and see, otherwise there is this overfitting issues and so on. So how do you address the fact that you need lots of training data? Is that an issue in your case?
I see. I use 400 data, 400 training data per single model, and so to extend our models, our test training data, we should train other more models.
So it's not that big of an issue in your case, is it? I mean, so from what I can make out, that you're able to handle, you can get accurate results with moderate amounts of training data.
Yes.
So that's your feeling. Okay, that's optimistic. That's nice to know.
Thank you.
Okay, I think we have time for one more question or comment. Okay. All right. Any questions? Okay, so if not, so let's thank Mr. Hayashi for a very nice talk. So the next speaker is Professor Girish Settler.
Yeah, I'm here.
Yeah, so yes.
Okay. Okay, so at the outset, I'd like to thank the organizers, both from IIT Guwahati and TokyoTech, for organizing this, and specifically Professor Banu Das for chairing this session, and all the other chairs as well. So it's really a great pleasure for all of us to be involved in such a noble enterprise. And I hope we'll do justice to this collaboration. And it's really nice to know that a publication has already resulted from this collaboration. I hope many more will be forthcoming in the future. So my talk is about a new technique we have been developing for the last several years. Well, it was new last several years ago, but now it's not new. But it's new in the sense that we noticed that people are still somewhat hesitant to fully endorse what we are doing. And one of the purposes of this talk is to convince whoever is not convinced to take this idea seriously. This is especially important because one of the editors of Physrev specifically told us that if you want to convince people, you should compare with DMRG. So I'll tell you what we are doing, and this talk is about the comparison of, so let me share, and it is basically, so are you able to see my slide? So can you see my PPT, please? Hello?
Yes, yes.
You can, okay. So as you can see, the title of this talk is a comparison of this new technique we have been developing called non-chiral bosonization, NCBT for short. N means NC is non-chiral, B is bosonizer, T is technique. Okay? So NCBT, that's what we have been calling it. And DMRG is of course density matrix renormalization group, which is a very powerful technique for studying interacting fermions in one dimension. Of course, we have started doing the DMRG simulations on our own using the existing open source software by the White's group in Irvine. It's called iTensor. But we are a little, we are a late entrant into this game, so we don't have that much of an expertise. So this comparison that I'm talking about is going to be a comparison with already published work in DMRG. So I'm not going to compare with our own simulation which is still going on, but rather I'm going to compare with an existing paper on DMRG, which I'm going to describe. Okay, so my collaborators, my first collaborator in this particular topic was my former PhD student, Joy Prakash. He's now in SN Bose Institute in Calcutta as a postdoc. And my current PhD student is Nikhil Dani. So I tried to persuade him to work on this as well. Hopefully we'll be able to, convince the naysayers in due course if there are any. Okay, so see, the whole point is that, as you all know, or maybe many of you know, because this is an expert audience, see, the bosonization is a technique which enables a very efficient analytical study of fermions in one dimension specifically, and where the interactions are as easy to handle as the free theory, because they tend to be quadratic in the, so basically bosonization is a mapping that maps the original fermions into a certain kind of bosons, so that the theory of an interacting fermion is mapped to a theory of free bosons. So what happens is that if you have a theory where you have interacting fermions which are mutually interacting, but on top of that you also have impurities. So typically what happens is that the interacting Fermi theory is exactly solvable in this bosonization language, provided the mutual interaction between fermions are confined to what's called forward scattering. That means that there is no sign change in the momentum transfer. So if two fermions scatter, they kind of move in the same direction as before. So the original fermion, so they don't change directions, but they change magnitude only. So that's called forward scattering. So if you only restrict your attention to forward scattering, then the model of interacting fermions in the homogeneous case is exactly solvable. But as you very well know, in the early 90s, there was a seminal paper by Charlie Kane and Matthew Fisher, which started the subject of impurities in a Luttinger liquid. So the idea is that, so what they did was that they, the conventional approach which they advocated was that you take this bosonization framework, which is applicable to studying interacting fermions, interacting with forward scattering interaction. You solve that exactly and use that as your starting point, and then you handle impurities as an afterthought. So you introduce impurities. So when you bosonize the system with impurities, what will happen is that in the conventional approach, the impurities will lead to a Hamiltonian which is non-local. So it leads to what's called a Sine-Gordon theory. So according to us, the main problem with this is that the impurities are thought of, they are introduced as an afterthought, that it's the interaction between fermions that treated very well, but the impurities themselves which cause so much drastic change in the ground state of the system. I mean, if you take free fermion and put in impurities, it just messes up the whole system. And yet such systems are, those are not even perturbation, they're drastic changes to the ground state of the system. And yet they're, introduced as an afterthought almost. But then, so the conventional approach involves using RG on top of this Sine-Gordon extra term, and then you try and draw your conclusions that way. So what I thought of several years ago was that that is not acceptable, because impurities certainly should not be thought of as something that's an add-on. So that should be done first. So the interactions between fermions is a kind of a weak thing. Even though qualitatively it changes from a Fermi liquid to a Luttinger liquid, it is still some kind of a Gaussian deformation in some sense. So the way we did this was to modify the Fermi-Bose correspondence in the conventional bosonization. And let me see if I can bring my laser pointer. So this is the conventional bosonization, which maps the field operators to a certain collection of bosons here. So the non-chiral bosonization is basically an attempt to modify the Fermi-Bose correspondence by introducing this extra term, which doesn't spoil the Fermi statistics. So the fermions continue to anti-commute and so on because of this 2 pi and so on, 2 pi I. So that 2 pi I will not bring in funny signs there. So the funny signs is already contained here. The -1 comes from here. So those of you who know bosonization know what I'm talking about. So so the whole point is that this rho minus y is basically it encodes the backward scattering. So we assume that there's a cluster of impurities close to the origin, and you have fermions that are going to tunnel through, and some of them are going to scatter back. So the back scattering is captured by this modification here to the Fermi-Bose correspondence. So we have a paper in a mathematical physics journal where we show that this doesn't spoil any of the relations that are considered sacred. Okay, so I can give you a whole bunch of reference. So we have published close to 8 papers on this subject already, all except in PhysRev, and I'll tell you the reason why. So that's the reason why is exactly the reason for this talk. Basically, the editor said you have to compare with DMRG. Okay, so this is the new Fermi-Bose correspondence. You can also look at it, somewhere at the back on my board also. So this new is the right mover, +1 is right mover, this is left mover. So this lambda is 0 or 1, depending upon whether this modification is needed or not needed, and so on. Okay, so the idea is that this chiral bosonization is rigorously applicable for this system where you have this infinite number of negative energy states which are filled up to some level. Whereas, of course, we study only a normal parabolic system where the states are filled up to Fermi level, and we look at something close to the Fermi points. So in some sense, these two are qualitatively the same, but there are some subtle differences. So let's not actually go into that. So the point is that to cut a long story short, because I have spoken about this earlier in the last Tokyo Tech conference. So we were already in the last conference, I pointed out that we were successful in deriving this, the most singular part of the density correlation function with interaction and with impurities in this really beautiful closed form. So this mod R is basically the bare reflection coefficient of the cluster of impurities near the origin, and VH is this Haldane velocity. So I'm talking about spinless fermions here, and this is the slow part of the, so this is a very new result in the sense that we are the first one to explicitly derive a closed formula for this. So this is the most singular part. And of course you may ask, like, how do you know this is the most singular part? That's we have explicitly proved this in a recent paper that was published in Physica Scripta in this year. I mean, it was already implicit in our earlier publications, but we felt it was it's necessary to make it explicit. So on not only density correlation, we can explicitly write down the entire full one particle Green's function. So you have different kinds of Green's function. When you have right mover, Green's function, and you have right, left, right, and so on. So and you see the various exponents here, gamma 1, p, q, capital X, and so on. And this is with spin, by the way. That was the earlier one was without spin. So we have done both. So now I'll just point out what. So all these exponents are explicitly expressible in terms of the bare reflection coefficient of the cluster of impurities and this Haldane velocity, which is in turn related to the forward scattering strength. So this is all already there in our earlier publication. So this is an explicit form for the Green's function. It's quite remarkable that you can actually write this down. So the claim is that this is the most singular part of the one particle Green's function, and the earlier slide was the most singular part of the slow portion of the density correlation. So now you can specialize to a case. So what happens is that you see, if you stare at these exponent, you'll see that they are not universal in the sense that they appear to depend upon the impurity strengths. So this is in contrast to what this conventional chiral bosonization suggests, that there is this famous cutting the chain and healing the chain. So that the claim is that if you have fermions which are mutually repelling, then an arbitrarily weak impurity gets amplified in such a way that the low energy physics is dominated by a scenario where that impurity is effectively infinite in strength. So basically, they claim that the exponents, there's only a binary thing. It's either the exponent is either infinitely strong or not there at all. So if the fermions attract each other, it's as if the impurity effectively disappears. So the fermions ignore the impurity and move about as if. So that's the conventional chiral bosonization approach. And now later on, I'll tell you the reasons why we feel that this is not very valid. And not only we are saying that there's a very influential paper by a group which has done DMRG with whom we have compared, also thinks that's not really believable. However, the vast majority in the community continue to believe that, which is why we are having trouble convincing them. Okay, so the idea is that there is a reason why the impurities, or rather the exponents, appear to be independent of the impurities, and that is that, you see, it is only the most general form of these correlation functions that have these funny exponents which depend on the impurities. However, if you try to look at any simplified version of this general correlation function, which is typically accessible through either exact solutions or numerical approaches, which typically involves, say, equal time correlation functions and so on, then all of a sudden you'll see that the impurities in the exponents, they cancel out miraculously, and you end up, so our formulas exactly say this, that if you look at say spinless fermions for say right movers and right movers, where x1 and x2 are on the same side of the origin, so on one side of the impurity, then you'll see that lo and behold, the correlation functions actually have an exponent, so they go as position to the power p plus q, and neither does p nor q depend on the impurity strength. Okay, so that's the whole point. So that this even here, so it doesn't depend on how you do this. So regardless of whether you do it as x1 times 2x1 or x1 plus epsilon, whatever it is you do, the impurity cancels out. So same with the right-left correlation function. Of course, this is identically zero in a homogeneous system, but then it's not zero when you have backward scattering from the impurities. And then you see that explicit formula also, that oddly enough, the impurity strength cancels out because we are looking at equal time correlation functions where x1 and x2 are in some sense proportional. So this is probably the reason why it's hard to pick up this impurity dependence of the exponents, because many exponents the impurity kind of surreptitiously cancels out, and then it's only in the most general form of the Green's function the impurity survives in the exponent. So I'll tell you, there is a let me get to that. Noting. Okay, so what is the main advantage of using NCVT? So basically it includes the presence of impurity right from the start. So that means the free theory plus impurity is exactly solvable, using trivial undergraduate quantum mechanics. But therefore, any method worth its salt should also be able to treat that system equally easily. Unfortunately, conventional bosonization cannot even handle free fermions plus impurities easily. That becomes a Sine-Gordon theory in the conventional approach, and that's not acceptable according to me. So our approach treats free fermions plus impurity as trivially as you would, an undergraduate quantum mechanics student would easily solve that as well. Okay, so we are not going to introduce impurities as an afterthought. It's encoded into the Fermi-Bose correspondence. So, so the whole idea is that we want to see if we can compare the results of NCVT, which we have rigorously proved analytically that they're absolutely correct. And so we want to see if we can compare with DMRG. So to do this, we have to, well, all the existing code deal with lattice systems. So we start with a continuum system, kind of, it's the reverse of what we normally do. We start with a lattice system and then map it to a continuum to do analytical work. But then here we started with, this is the analytical model that we have used to study with, to do NCVT with. So the non-parallel bosonization studies this. So you have this right movers kinetic energy here, and this is the impurity. So this is the backward scattering, the right becomes the left because of this. And then this is the conventional forward scattering. So there's right plus left. So there's a conventional forward scattering between fermions, and this is the, when fermions bounce off the impurities, this is what you get. This is the impurity Hamiltonian, this is the conventional kinetic energy. So the idea is that you want to sort of latticify this system, so go from the continuum to the lattice. So you make this approximation that k is sine ki by a, where a is very small. And then you can convert this to a lattice system. And this is what we look. So instead of R, we can think of it as up, because the codes typically deal with fermions with spin, but single species. So here, a right mover and a left mover is like up spin and down spin. So instead of, two species like right, left, we have one species but with spin. I mean, it's just terminology. So, so we kind of identify up as R and down as L, and then you get this, and then this you can directly dump onto your DMRG code and see what you get. So that's what we are running now. But then, the computational resources required to extract Luttinger liquid physics from DMRG is considerable. And you can, if you read the literature, you'll see that it's a very non-trivial task indeed. So, so instead of, well, we are going to do it ourselves, but then since we don't have our own results, we are now forced to compare with already existing work. And one of the important works in this field is this DMRG studies of impurities in Luttinger liquid. This is the title of this paper, which was published in Progress of Theoretical Physics many years ago. And they use DMRG and their own favorite approach they call functional renormalization group. And what they conclude is that the universal physics predicted by Chern and Fisher that only sets in at extremely long and experimentally irrelevant length scales. So, so this is an important point they make, that that they are actually not able to reproduce the universal physics produced by conventional bosonization. So, so you can see in this plot. So, okay, I'll get to that plot later. So the other notable work.
Excuse me. Yeah, you've got 5 minutes.
Okay, I'm done. This is
okay. Fine.
Yeah. Okay. So, so there's this other approach this other work which we haven't compared with, but it's notable as well because they use the infinite DMRG for studying continuum systems directly without doing the lattice thing. So, whereas the you see the non-chiral bosonization gives you so now what we're going to compare. So this paper, the paper by Scholwok et al. They actually do a DMRG for the density of states exponent near the impurity or at the impurity. So of course, our non-chiral bosonization gives you an explicit formula for this exponent in terms of the the Luttinger parameter, the homogeneous Luttinger parameter K rho, and the Baer's impurity reflection parameters. So. So now you can see, of course, for the half line. So if mod R is 1, which is the perfect, infinitely strong impurity, that agrees exactly with Chern and Fisher. So there is a reason why a non-chiral bosonization is going to agree exactly with Chern and Fisher when the impurity is either infinitely weak or infinitely strong. We have rigorously proved this as well in our several papers. So, however, in between, we differ. And so now the question is, how do we compare with DMRG is the question. So now if you stare at this plot, so these solid diamonds and triangles and squares are the DMRG simulations. So you can see that the solid circle corresponds to the impurity strength being 1. So this in some units, and the solid square is impurity strength 2, and the solid diamonds is, so this is the DMRG by Scholwok et al. So so this solid diamond is 4, and then the solid triangles is half line, that is infinitely strong impurities. So now these horizontal solid lines is NCBT. It's the horizontal solid lines are non-chiral bosonization. Of course, the x-axis is the number of sites. So we have, our theory is for the thermodynamic limit where n is infinity. So strictly speaking, we should look at n very large. But then you can see already that the solid shapes are always hovering close to our lines. See, whereas if you believe the Chern and Fisher result, they should all converge to this b equal to infinity result. So this thing, of course, this seems to go up, but then you see this actually comes down and touches our line exactly. It doesn't seem to be going up at all. So it's like coming down the. See, what is diamond? Diamond is 4. So diamond is actually coming and touching our horizontal line, which is the non-chiral bosonization result. So same here also. So the thing is that, of course, you can say it's still inconclusive because we have to really extend this beyond this. See, what I find suspicious is that this paper kind of stops here when it comes to DMRG. These the ones which are not filled in, they are their other approach, which is called functional bosonization. So which is not really numerical; it's more sort of analytical. So, the point I'm trying to make is that I feel that there is, by staring at this, there is a case to be made that the impurities are in fact not universal, and it's also consistent with the remarks they have made in this paper as well, that the universal physics really sets in at experimentally irrelevant length scales. And I feel that they're saying that because they don't want to antagonize the community. Deep down inside, they probably don't believe that there is anything universal. And we certainly don't believe and we have rigorously proved this in our various papers. Okay, so I'm going to wrap up. So the idea is that we feel that by staring at these plots already, that the non-chiral bosonization results show that the exponents are in fact not universal. They depend upon the impurity strength, and this is consistent with the work of Scholbock on DMRG, and the analytical papers we have published, 8 of them. The most recent one is this, which explicitly does a perturbation theory using conventional conventional fermion perturbation theory, and compares term by term with the corresponding expression. So you take the non-chiral bosonization closed form result and expand that in terms of the fermion coupling, and term by term we compare with conventional perturbation theory. There's Feynman diagrams, and each term matches term by term. So in fact, up to second order we have done. A second order is enormously complicated, the expression, and yet every term matches. So the second order term is so complicated, that's remarkable that it matches so well. So we feel that there's absolutely no reason to disbelieve NCBT, non-chiral bosonization, except that editor of PhysRev feels that this is not good enough. You have to do DMRG. We have done that as well. So I hope if they are listening, I'm sure they're not, but if they're listening, they should take it seriously. So I thank you for your patience, and I'm open for questions.
Okay, so thank you very much, Professor Settler, for a very nice talk. And now we can have some questions from the audience or comments. Yes, we have time for questions. So please go ahead if you have any questions.
Yeah, I was going to share this. So this is the paper that we wrote recently. So it was the Physica Scripta thing.
Mm-hmm.
So you can see here that we have in the appendix, we have explicitly shown by comparing term by term. So if you take this density correlation, you do this conventional fermion perturbation theory up to second order. So you can see the second order term is so enormously complicated here. So this is what it is. And so yet, can you see this paper that I'm able to see?
Yes.
Okay. Yeah. So this. So if you take your the non-chiral bosonization result, expand up to second order in this fermion coupling, what you're going to get is this expression, and this is also the same expression you get if you do conventional fermion perturbation theory using Feynman diagrams. So it's really remarkable, and this is the reason why this deserves to be taken seriously. We are in our earlier paper, we showed the same thing for Green's function. In fact, we did even better. We showed that the Green's single particle Green's function obeys the exact Schwinger-Dyson equation without, not perturbatively, exactly. So it's provided you, chop off the less singular parts. So there is a precise sense in which our results capture the most singular part of we have explained that. I don't have time to go into that. So you take the Schwinger-Dyson equation and chop off the less singular parts, and the Green's function obeys the truncated Schwinger-Dyson equation, which only takes into account the most singular parts. So I feel this deserves to be taken seriously. So I'm open to questions. If there are no questions, I thank all of you for listening and for participating in this conference. And thank Professor Das for chairing the session.
Okay, thank you, Professor Settler, for a very illuminating talk. I think, I'm sure the audience would have benefited in many ways. Okay. So that brings us to the end of the third session, which was the final session of today. So maybe I'll sort of hand it over now to Professor Ghosh or Professor Kuze for any comments.
Yeah, thanks everybody for very nice talks and basically keeping the time. It really went, the first day really went in a very well-organized way, and we didn't have any technical glitches. That was one of the concerns, certainly. So thank you all. And I think the participation was quite handsome. I could see there are several students attending. And so thank you, everybody. So Professor Kuze, if you want to add something, you may please add.
Yeah, I agree. Yeah, it went very smoothly, and the time was kept thanks to the chairs. So yeah, we see in the second day, which is Thursday, not tomorrow. Yeah, the same time.
Yes. So that will be 9 o'clock Indian time and 12:30 Japanese time.
Yes. Yes.
Okay.
So
Thank you very much.
thank you very much.
Nice day.
So I will stop recording.